Welcome to ET Auto Masterclass on System Engineering and Simulation for Interdisciplinary Teams at Automotive Organization. We all have seen this pandemic and crisis has pushed us to rethink our processes when it comes to engineering, when it comes to manufacturing, because a lot has changed from what we had in pre-COVID era to the post-COVID era. When it comes to product design and development, the demand from the consumer has also changed, the kind of features they are looking for. That means you have lesser time to market your product because of the change in demand. A shorter time to market means shorter time to design and produce your cars or automobile parts or anything. So what comes out as a protagonist in this is the technology. Technology, especially digital technology, is going to be the at the center of entire change. And if you talk about technology concept of system modeling and simulation, that helps in evaluating and balancing potentially conflicting performance attributes such as thermal management, operability, drivability, or fuel efficiency from early development stage till the final performance validation and controls and calibration of any product. You can rapidly create heterogeneous system simulation architectures and share your model with the global engineering team. In order to provide an understanding of the system modeling and simulation for Indian automotive industry, etauto.com, in association with Siemens and subject matter experts from the domain from around the world, we will be providing a day-long session today when you will have an in-depth understanding of system engineering and simulation for interdisciplinary teams at automotive organizations. So let's kick off this session with the first presentation, and I would like to invite for the first session Mr. Frank Populus, Managing Partner, SMS Think Tank, and Mr. Edward Ludzinski, CEO and Managing Partner, SMS Think Tank, on system modeling and simulation as integral part of design and transformation. Over to you, Frank and Edward.
Thank you very much, everyone, for joining us today to our presentation on systems modeling and simulation as integral part of digital transformation. This presentation is part of the masterclass on systems engineering and simulation for interdisciplinary teams at automotive organizations. My name is Frank Populus. I'm the managing partner and co-founder of SMS Think Tank. My co-presenter today is Ed Ludzinski, CEO and co-founder of SMS Think Tank. SMS stands in SMS Think Tank for Systems Modeling and Simulation, and our focus is to help our clients to enable sustainable innovation by improving engineering maturity. Let's introduce ourselves briefly before we start with our presentations. First, Ed, please.
Thank you, Frank. Hi, my name is Ed Ludzinski. I'm the CEO and co-founder of the SMS Think Tank. I began my career as a manufacturing engineer, NC programmer and tool designer right out of the university with Burroughs Corporation, which is now known as Unisys. In 1978, I joined IBM in the Kingston, New York laboratory as a research and development engineer and spent 32 years with IBM practicing systems engineering. Immediately after that, I joined Dassault Systems and assisted them in developing their systems engineering practice for the Americas. I serve on a number of committees worldwide, in particular NAFEMS and NCOSI, and this is just for reference. I also participate in a number of other not-for-profit organizations to promote system modeling and simulation. Back to you, Frank.
Thank you. So, as mentioned, my name is Frank Populus. My experience ranges for over 2 decades in the automotive industry on the tier 1 side, and I had exposure in that capacity to all major OEMs worldwide, might it be in the Americas, Europe, and Asia, and collected a lot, of course, of experience on that subject, and especially with focus on simulation and systems engineering. And similar to Ed, I also participate as a volunteer in non-for-profit organization like NAFEMS and NCOSI and co-organization as well. With that, I would like to start to get into the content of today's presentation. First, we are getting in setting the stage, and we'll talk about the engineering landscapes using references to the automotive industry. Then we go into the details on the digital transformation, talking about the case for systems modeling and simulation, the systems engineering approach in the context of systems modeling and simulation, similar when we are talking about the value of systems engineering, and focusing under the term of digital transformation, achieving sustainable information. To wrap up our today's presentation, we will talk about the power of end-to-end approaches in supporting companies in their journey of digital transformation. Let's start, in order to set the proper stage, with looking at the engineering landscape, the way we are dealing with it today. We will look at the hype of the emerging technologies, business challenges, and the associated market trends and needs. As examples throughout this presentation, we will use references from the automotive industry. There's lots of hype about technologies associated with digital transformation. We picked for highlighting purpose here on that slide the digital twin, since it is playing a key part in the future of the automotive industry. When looking at the Gartner hype cycle for emerging technologies from 2018, it is interesting to see that the digital twin is currently only at the peak of inflated expectations. This is when looking at the digital twin overall. When going into more details, one can see that there are pockets in the various industries that are further ahead or still on the upslope, but this would be part of another discussion. Here we want to highlight a few technologies that are closely linked for this example, digital twin, like IoT platforms, 5G, autonomous driving capabilities of varying levels, various levels of AI, artificial intelligence, and of course data security needs to have a central role when talking about the sharing of information and collaboration throughout the supply chain and across ecosystems. Again, we highlighted the digital twin here as a key capability for future application in the automotive and transportation industries that needs to be part of a long-term strategy of the digital transformation in those industries. Typically, various teams of engineering-driven companies look at a problem from their domain-specific perspective. The picture here portrays this from the lighter side. Still, it highlights the fact that even though all sit in the same car, they don't see the system vehicle, but as a vehicle, as a system as a whole, but only their respective silo. This is a prime example that if system thinking is not part of a company's culture, it is difficult to live it. This brings us to the vision and the vision statement objective. We put this at the very beginning of this presentation to highlight the importance of system thinking in the terms of systems modeling and simulation that it needs to play in our modern engineering and business environment. Throughout the presentation today, and by the way, also when we have our overall systems modeling and simulation education program, which we have developed, it will become clear what is needed to formulate a good systems modeling and simulation vision and enabling strategy. First, let's set the stage looking at some of the major market challenges. I would like to highlight again that digital transformation and systems modeling and simulation is in the back of our mind all the time when talking about those challenges. Global economy. We are more interconnected than ever, even if we don't see it directly. And I would like to make a comment today with the pandemic of the virus we have currently worldwide. We see this as in our day-to-day lives, what is happening, how we are interconnected with each other, and what impact we see, challenging impact on our not just personal lives, but also the commercial interconnections we have worldwide. Faster than ever changing and evolving technologies. The pace of technology development and corresponding model changeovers has dramatically increased and is in certain industries an almost ongoing phenomenon. The age of data and information. We rely for most of our activities on data. But not only do we want to have access to the data, but also want to make sure that we make use of it, connect it, so it can become information. And I will talk about this at a later point when we're talking about the maturity, how this comes together, data and information and insights, by the way. Practitioners are finding it increasingly difficult to communicate their needs to management. Way too often there is a disconnect between management and technical experts in the various businesses. Management is often stuck in traditional thinking and has a lack of understanding of modern approaches in order to make use of latest technologies. Digitalization, visualization, collaboration. In our virtual-driven age, we need to ensure data and information is easily and digitally available and processable. It can be looked at and understood in an easy manner, and we are able to get in contact with each other seamlessly at all levels of our lives, might it be professionally and personally. The complexity issue, what was mentioned before, makes everything, might it be a product or a service, more complex. This challenge needs to be addressed throughout the entire life cycle, starting at conception, ideation, throughout the development, and continuing into service. Especially in the automotive industry, the complexity saw a dramatic increase over the last decade in particular. This was driven mainly by embedded electronic systems that are now being part of the vehicle system. And when you look at here at that picture and you see how complex, much more complex even the modern car today is compared to the space shuttle. Probably a lot of people would not imagine that. Then looking even further into modern vehicles that are equipped with tons of sensors, the increase in complexity is accelerating. And since there typically is no proper systems engineering part of the development, deployment, and service processes, this can become, for the manufacturer as well as for the end user or the customer really buying the car, a nightmare. And when looking at this here, what I just brought up on the slide, there are currently typically 60 to 100 compute units on a car with various about 6 to 8 independent operating systems, isolated independent systems. And that of course increases the complexity and the costs for a car. And this makes it much, much more difficult to upgrade those systems in a meaningful and safe way. To address the mentioned challenges, some of the most critical engineering trends are, as we are going through now in the next couple of slides, increased complexity. Not only is this a market challenge, it is followed by an increased complexity that addresses the challenges on all levels and throughout the life cycle. And I'm not going into all the details of the boxes I'm showing here. Demand for flexibility and choices. Customization is common practice today already and will increase so even further. Fulfill the needs of every particular customer. Improve product quality and robustness guarantee. This needs to happen upfront before a product or service is being launched. And thus we are talking about the virtual aspect. And this is when we are talking about digital transformation. So meaning to achieve all this, what we talked above, the various industry with their associated processes and beyond need to be virtual more than ever. This goes well beyond traditional simulation departments. It extends into all aspects of an enterprise as well as normal daily life. And I highlighted digital transformation and sustainable innovation. And when we are talking about sustainable innovation, from a business perspective, organizational culture and processes need to be established that enable an innovation environment that guarantees sustainability for the business on the long run, despite the ever-changing, from a simulation perspective, we know the word boundary conditions a business is operating in. The traditional basics and the basic principles still hold true. Companies are operating on an ever leaner level. There's an ever-growing demand of accountability. The business climate is ever more fast-paced and demands a constant development of new, improved, and efficient products and processes. Traditional technology, process or product, as well as focusing on just those elements without proper integration and consideration of infrastructure and execution is not sufficient anymore. For examples, indicators for those new demands are the following megatrends, as I show here already on the screen for the automotive industry: electrification, autonomous driving, and mobility as a service. To continue on the thought of sustainable innovation, there are some of the major trends that need to be considered to achieve sustainable innovation. And on the top is system modeling and simulation. This is an essential piece for the digital transformation for engineering-driven companies. The definition is mentioned here only. It will be discussed later during the webinar in more detail. IIoT in Industry 4.0. The operational element takes more of a center stage within digital transformation initiatives and its linkage to the overall virtual engineering efforts. Not only that we are starting, we are already in a new era of manufacturing. Big data and IoT, not only manufacturing, but even more so in our current time we live in, and we are living in an experience-driven environment. In order to account for that, lots of information needs to be collected and analyzed. This is resulting in the way we collect and distribute the data, and we also need a new infrastructure in order to support that. Iterative and collaborative approaches. What was mentioned before requires new iterative and collaborative approaches. They are closed loop approaches and span not just across domains within an enterprise, but also across organization and entire supply chain ecosystem. And cognitive engineering. And I would like to highlight this here. It is the highest maturity level. Here is where we start really to talk about advanced optimization and analytics capabilities, where predictive analytics is part of it. There are, of course, other elements and capabilities associated with this maturity, such as deep learning and digital twin, to name a few. As indicated earlier, we rely for most of our activities on data. But not only do we want to have access to the data, but also want to make use of it. Connect it so it can become information. It is a competitive advantage. How fast companies access and make use of the data. At the top level, we are talking about innovating at the speed of thought. We will get back to this later during the presentation. First, over the next few slides, let's have a look at some findings in this digital space and how they are associated with the challenges and trends we just discussed. Talking about the business pressures which are driving us to simulation-driven design. We need to differentiate ourselves. So that's a competitive pressure right there. We need to put smart features out there, top level. Of course, we mentioned that before, traditional principles hold true. Shorten the development schedules, cycle. We have to add greater innovation to our products and lower cost. And interestingly, the lower cost is not the first topic. It's really about differentiation, features for the customer, innovation. Please keep that in mind. Next, when we are talking about the complexity from a system design perspective, we talked about it. Top level, it is more complex. That is challenging. Early identification of a system level, that is where we need to shift it to. We will talk about this still. Cross-functional knowledge is lack. We are talking about that we need to overcome the silos and we need to predict system behavior. And you see here quite a few are saying it is a challenge to do so. And one of the things why it is challenging, because we don't have a proper understanding of the requirements. So since we are talking about, especially with the focus on the automotive industry, let's use some examples from various companies, OEMs. We know all major OEMs have had visionary concept vehicles put out into the public to view, to gauge the reaction of the end user community, as well as to show their leadership in the various areas they are targeting. And here you see what I mentioned before, entertainment or interaction, experience-driven environment for the end user. No one is focusing on an engine anymore. It's really how you experience this, how you interact with that. So that's an example from Mercedes. Similar when we are talking about Honda, the Acura brand. What we can see and hear is, and I focus please at the top right, the text box. There are a few holes in there, but I put those holes on purpose in there. The car of the future represents an automotive revolution in shape and design for inside interaction. But the discussion everyone nowadays has goes a huge step beyond that. Before we go to that step, let's look also, the Indian market made a huge step forward over the last decade. I followed this through my business trips and interaction with that market very closely. Here, when you look at some of the examples from Tata Motors, we are talking about very good design ideas. We are talking about safety, approaching it from a virtual perspective, and you see the airbags there as well as everyone else has. So we are not just talking about emerging market, we are talking top-notch technology also on the Indian market available. We are talking about experience, kind of infotainment system. We are talking about smart technology, which is represented on the lower left. And of course, when you look at this full electric vehicle, so that the whole thing is available and everyone is working towards that. The question is, and this is, now let's start to fill in the holes. The autonomous car of the future represents an automotive revolution in shape and design for outside interaction, not just the inside interaction. So this we have to keep in mind. And on top of that, in light of the topic of our class today, what does this have to do with system modeling and simulation? What will the drivetrain of the future look like? How will the customer interact with the vehicle? What will be the experience of the end user? And how will the OEM, the car manufacturer, contribute to this experience? And I think one of the best examples is when we are talking about modern approaches is Tesla. Of course, I could have put a Model 3 or the Model Y on, but I thought really from a differentiation, even from a shape perspective, the Tesla Cybertruck is a good example. Again, what does it have to do with system modeling and simulation? So this brings us back to the complexity issues in hand. System complexity is increasing. We mentioned that before. Required time to market decreases for most of the industry, definitely for the automotive industry. Without disruptive changes, this is an impossible equation to solve. The main culprit, and we mentioned that before, is software complexity. The electronic industry, what you see here on the graphic, was able to manage its increasing complexity over the years pretty well. You see the red bar there. The aerospace industry definitely needs to change if they want to be able to bring competitive product, system, and services to the market. And you see this with the bluish line going, or the area going up. They definitely need to change. And when you talk about, for instance, the Boeing 737 MAX, they had problems because they did not do a proper job when it comes to system modeling and simulation. For the automotive industry, we had for a long time another positive picture. Actually, the green was going down. This started to change with the trend going towards connected vehicle, experience-driven end users, and much more. Especially the push for autonomous capabilities added another level of complexity. And this is, again, we have to keep that in mind when we are talking about the automotive industry. When we are looking at the landscape, one of the major problems companies are facing is what is shown on this slide here. The various domains and departments operate way too much in silos still. With the increasing complexity and its associated challenges, if not outright a train wreck, upcoming problems are very much predefined. So we mentioned before that there are quite a few ECUs, compute units on a car, on a vehicle system, and operating systems in a typical car nowadays that need to be consolidated to ensure a smooth development and deployment process of the vehicle system, as well as in-service support. To achieve such consolidation and complex system integration, and not just, for example, within the vehicle, but also the vehicle operating within its environment, socially and commercially, systems thinking need to be enabled. Just following the previously established principles and defined processes is not sufficient anymore. Those need to be adjusted. let's have a look on how systems engineering in the context of systems modeling and simulation can help. For that, let's use the slide we looked at before, but from a different angle. This is where we ask ourselves the question, are we integrating the various systems properly? Aren't we just releasing the products too fast? Do we have the proper development processes in place? Do we do a proper systems engineering? And eventually we say, do we have a proper model-based systems engineering approach in place? A few additional comments here from a market analysis perspective. And this is from a software perspective when we're looking. Definitely more complex and very important interdependency. This is what we need to look at and consider properly. And this is when we are talking also about proliferation of tool change and modeling language as a barrier to effective traceability, etc. So we're talking right away about standards here, by the way. Systems modeling practices. We need federated approaches. And again, we are talking about interdependency. We need to integrate a requirement, logical, functional, and physical approaches. It has to happen cross-domain and multi-domain. But before we go further into the midst of our presentation, let's have again a look at the current engineering landscape from a lighter side. How much is system engineering part of our current activities? And what is interesting, actually, those graphics or cartoons were drawn up already in 1997, over 20 years ago, and is still holding true today. With that, I would like to get into the portion of the digital transformation, and Ed will take over from here.
Very good. Thank you, Frank. What I'm going to do is I'm going to discuss the case for system modeling and simulation. How do we define this? What the systems engineering approach is, and then we're going to go through the benefits. So let's take a look at the case for system modeling and simulation first. What is it? What is system modeling and simulation? So many people are confused because they think about maybe it's Mbsc, maybe it's systems engineering. Well, in all my experience since I've first heard that acronym Mbsc, to now, I have come to the realization that it's probably the most used and abused acronym in the history of engineering vernacular. So we are here from a vendor agnostic standpoint to talk about what is system modeling and simulation. It is a blend of simulation and analysis that includes finite element analysis, computational fluid dynamics, multi-body dynamics, Excel, and so on and so forth. Things that are usually represented by NAFEMs, if you're familiar with some not-for-profit organizations which deal with that type of technologies. And it's a blend of systems engineering, which deal with requirements, functional descriptions and decomposition, controls, dynamic behavior, V&V, verification, validation, all including cloud-based and analytics. That's very important. And what that does all together, that provides the foundation for what we call system modeling and simulation. It is a blend of many different technologies, but most important, it's a holistic approach to the solution of a problem. We're going to get into that in more detail, especially if you're not familiar with that V model. So let's talk about what the definition is. The definition of system modeling and simulation, I can read this just as well as you can, but let's concentrate on interdisciplinary, functional, architectural, and behavior models, an organized set of components, subsystems, systems, and processes. This actual definition was developed by the System Modeling and Simulation Working Group. Now, what is that? That is a collaboration between the International INCOSE organization and the International NAFEMS organization. And between those two, they spawned a working group which will share the technologies, the solutions, the challenges, and this is one of the outputs of how we will define the terms and definitions, so we're all talking the same language. Let's investigate this V model a little bit more. Now, the V model is not actually your process model. It's a way to describe how you're going to incorporate the concept of operations from a stakeholder to providing the final product. So let's say, for example, we have a demographic which would like a car that is very good on mileage, gas mileage. It's very good on, let's say, the size of it. It's trendy. So, you have these concepts of operations which are developed from these stakeholder needs. And from those, you would derive requirements. I'm going to pause just for a second and talk about requirements. Because requirements, with all the customers that we have, or the majority of the customers, they struggle with requirements. There are some people through the years that Frank and I have been dealing with that really don't have well-defined requirements, and they don't know how to write the requirements. There are people, there are laggards out there, and that there's an old phrase which says garbage in, garbage out. So if you don't have properly defined and written requirements, how can you define a test case to see if you have approached or reached the satisfaction level of that stakeholder? So in this V model, we define the requirements. We functionally decompose those: functional, performance, regulatory. There's many different types. We functionally decompose those, and we logically lay them out and build a physical model. Physical model could mean code. It doesn't have to be a physical 3D model. It could be an output, like I said, from, let's say, some control code. That could be a physical model. And then we perform a verification and a validation on that, and that is signed off and released. But this is iterative. What's very important here, that if you look at that circular loop, the ideation, requirement assessment, design and product development layout, all the way through to manufacturing, and then finally the retirement of the product. This is iterative, it's global, it's in the loop. And what it does is it incorporates all the disciplines in parallel, not sequentially. They're iterative, and all of these have to be across those silos that we discussed. And we're going to get that in more detail. So what is the foundation of when we look at system modeling and simulation? We have to take into account that it's the realization of merging systems engineering principles with CAE, but we're also dealing with organizational and cultural principles. What that means is organizational, there has to be a cultural enhancement, a cultural transformation to look at not component level engineering, but to look at a problem holistically. And those are some cultural challenges. We have determined through extensive work that that is part of organization, process, and technology. Let's look now at what we refer to as a digital thread. You might have heard that phrase, digital thread, but it's the promotion of the effective utilization and advancement of requirements, guided modeling, and simulation technologies. That's from low to higher fidelities, from 0D to 4D, logical and physical models over time. This is commonly called that digital thread. This is in order to predict and optimize behavior and performance, and it's respecting other disciplines. So it may include those silos that are traditionally built that it's very hard to communicate and collaborate with. But what this does, this digital thread, is it includes this model-based methodology and thought process to share these descriptive models to make life easier for everybody. This is hard for a traditional engineering organization to adopt, but there are ways to develop these techniques. Let's now go to the maturity level. And what we have, if you look at that pie chart, we have a vehicle lab. That means test and break. We have a bench lab, which means, okay, we're going to have some of those virtual aspects there, but we're a little bit better than just saying, Okay, test break. And then we have that virtual lab. The virtual lab is more upfront simulation. This is what the OEMs that we work with are now demanding, more upfront simulation. So we have worked with OEMs and suppliers that are reactive. They're laggards. And if you notice, they do a lot of test and break, vehicle lab. Next, we have those that are adaptive. And these are traditionally run businesses where they're doing less of the vehicle lab, more of the bench lab. And if you notice, there is a dramatic increase in that virtual lab. And then we have the proactive. The proactive, they are linked to modern businesses that are leaders in their segments. Look at the distribution of the upfront virtual lab now, the upfront simulation. They are proactive. The top level of this is cognitive. And we're going to be talking about cognitive in a little bit more detail. But this is the maturity level where customers would like, this is where they would like to be in the future, to respond to their customer needs, to those stakeholder needs, to have more of an upfront view to reduce the schedule slips, the reworks after the design phase, the field failures, the liabilities, the risks, the warranty costs. And so let's go on and let's talk a little bit more about the evolution of systems. So when we get into cognitive, we're looking at various systems of systems. And in this case, we're creating greater engineering challenges, but what we're doing is we're incorporating different processes into how we're generating these systems of systems. For example, we have nature, we have society, we have the environment, we have space, we have communications. But what cognitive is giving us is the ability to look at, for example, if a car is operating in some, on some roadway, we can flash environmental updates, like let's say, for example, nature, mud, gravel, concrete, what is it good or is it bad? Society, congestions, backup, accidents. And we can let the participant, the vehicle, know what they're going to be dealing with. And this is going to be in a real-time environment. This is a feature that is beyond that autonomous. We're looking at what we can do to make not only the experience better, but to reduce fatalities. So let's take a look at the systems engineering approach to this. The objective here is to introduce that systems engineering V. Some people might say, I am sick of the V. The V has been around since Bell Labs. It's there's got to be a better way to express it. It is right now the universal way that people are communicating. We have come up with alternatives to this, but for this Mbsc type of approach, we're going to stay with the traditional V so everyone has the same basic foundation and understanding. So we want to provide that and understand what the three key elements that form the foundation of a systems engineering approach are. And we would like you to become more comfortable with the systems engineering V and what its driving principles are, and to understand what each block in that V approach is, because many people don't understand the flow. Okay, let's actually take a look at the very beginning. We were talking about requirements. Now let's talk about data first. And that is typically what we do is we look at what a customer situation is. And this is pretty much universal. And this is what we recommend to people that are starting their journey into Mbsc. And that is, you must look within your organization. Determine your requirements first. That is the center core. If you don't have well-written, documented, authored requirements and a centralized database that can be utilized, that could be accessed and managed easily, you've got a very, very, very difficult battle ahead. So the as-is situation usually involves scattered and disorganized requirements. Maybe they're in Excel spreadsheets, maybe they're in PowerPoints. Maybe they're in Word documents. Maybe they're on napkins. Maybe they're in somebody's head. There's also duplications to deal with. The inability to locate the information. How many hours, days, weeks does it take to find the information that you need? That is not a good start if you're going to embrace systems engineering and especially Mbsc best practices. How do you classify them, integrate them, and their workflows? How do you perform traceability analysis? There's a lot of what ifs here. There's a lot of questions. So what we promote is, and we strongly advise people to look within, determine what your as-is situation is, then determine where you want to be. Where are your requirements and documents centralized, organized, and related? No, limited or no duplication, easy retrieval, and the integration across all processes that are related, and you have full traceability and impact. So it's going from a very dysfunctional environment to a well-organized environment. This is the major first step that must be realized before any company can proceed with Mbsc. So what we're going to do is we'll talk about the three key foundational elements to a solid systems engineering approach. Now, I'm not going to read every word on this slide. There's a lot, but it's made for reference, so you can digest this at your leisure. I'm just going to say that the first thing you need to do is connect requirements, design, and test for multidisciplinary collaboration between those silos that we talked about, and enable systems engineers to manage requirements at architecture, design, implementation, and test. And then there are some bullets underneath that which really describe in more detail how you're going to go from that solid SC approach to Mbsc, which is really a subset of systems engineering. You need to verify as design and as built product against the design and requirements throughout the product lifecycle, not just in development, but all the way through verification, manufacturing, and retirement. You need to enable validation of lifecycle assets from requirements to end of life as they're created and as they're changed. I did say that in my last sentence, but also key upon this, as they are created and changed, even as they near the end. For example, when we deal with digital twin after, let's say, field deployment, there can be requirements that are created or changed. You have to be able to deal with that. That's why the earlier statements about requirements and data management hold true. Let's take a look now at the systems engineering V in the life cycle. We have, as I mentioned, the concept of operations. You can see that at the upper left. And then we go and we have system requirements. From that, we derive requirements. That becomes iterative. That's what that small v represents, where it's requirements, model, analyze, requirements, model, analyze. That goes all the way down through the V at the bottom and all the way up to the top. It's iterative. What we are doing is we are saying RFLP, requirements, functional, logical, physical. And we look at the left-hand side of the V where we define and decompose that RFLP. And if we look at the right-hand side, we're actually doing the component testing, and we're doing verification, validation. And then at the very end of that, system acceptance. Now, before we go on from the slide, notice some very important arrows. From the concept of operations, someone in that enterprise needs to develop the system validation plan for acceptance. Have we met the stakeholder needs? From system requirements, when they're derived, there has to be a system testing or system verification plan developed. Are we meeting the subsystem requirements as dictated by those concept of operations and the regulatory requirements and derived in functional and performance and so on? Then we get into the high-level design. We have subsystems and subsystems and subsystems, and we need to verify that they are performing as we are expecting. even into component verification, where we do that component testing. And on the right-hand side of the V, we're going integrating and recomposing the actual process and product. We want to do in a virtual environment as much as we can. The key is this must be done with respecting the various organizations that are designing this. This should not be sequential. This should be upfront, flexible, in the loop, accountable, transparent, and realistic between the mechanical groups, whether it be structures, the electrical group, the electronics group, the software group. So rather than working sequentially, the Mbsc dictates that you have a common plant type model, and I'm going to focus on plant model. And it's a model where it's a descriptive model where other models could be generated from that for software, electronics, electrical, and mechatronics in parallel as much as they can. So the benefits, we'll be getting into that, but they're significant. Now we should look at the value of systems engineering. This is going, I hope, to be very interesting for you, because with the value, we get into some let's say, challenges between personalities. See, systems development, design process, these processes, they need to be flexible so they can reduce, the cost of impact introducing changes. And systems engineering has its greatest opportunity to influence design decisions early in the systems design and development cycle. So we look at that graph, or those graphs, and what the key message is that typically 80% of main engineering decisions are taken within the first 10% of the project lifecycle. How much money should be dedicated toward systems engineering, or a subset of that Mbsc? Many different studies from INCOSE have revealed that approximately between 15 to 20% of the development budget be dedicated toward those activities. Now, managers rely heavily upon assumptions about system requirements. Assumptions. And many of these are constantly too optimistic. There's large gaps, and even prior to beginning. So what we need to do is we need to educate the decision makers at all levels. And we'll be talking about that next. What are some of the benefits to systems engineering and Mbsc? I can read every one of these to you. Better educated decision making, reduced engineering changes, reduced introduction costs, reduced recalls. Okay, now, if you went in to upper management, executives, and you said this to them, they're going to immediately look at you and say, quantify it. How much? What is the number? Systems engineering, and especially within that Mbsc, is very hard to quantify. How do you say you're going to increase sales? How are you going to say you're going to reduce schedule slips? How are you going to say you're going to reduce failures throughout the development process? I mean, they're going to say you should have identified that anyway. Well, what happens is you can take the best engine and the best transmission and put them together, and you can have a total failure because they weren't modeled properly within a model-based systems engineering environment. So it's difficult to quantify what the benefits are. This is why upper management must be educated in the value of systems engineering, so they understand that they're meeting stakeholder requirements without the pains that they've traditionally experienced. Let's now go to some benefits that were proven empirically. I mentioned that it's hard to quantify. However, with the customers that have adopted model-based systems engineering best practices, they have reported this. So this is derived empirically. They said that they've increased revenue between 2 and 5% in the end. They took the risk of implementing Mbsc. And from that, or a portion of it. Remember, there's a point of diminishing returns when you implement MBSC. If you try and throw the entire organization into an MBSC transformation, that's a train wreck. Start small, crawl, walk, and run. So the people that have implemented various MBSC best practices at various stages have seen these benefits, range of benefits in increases and also reductions. But notice how wide that spread is, because this is a report that has come out where it's merged aerospace, automotive, consumer packaged goods. It just includes so many that the spread is very, very large, but it's to give upper management and the executives an idea that, yes, this is what better looks like. Frank, I'm going to now hand it back to you.
Yeah, thank you, Ed. With that, kind of, you talked about the benefits and we talked about understanding of the upper management. And of course, we need to lay out a path, because from a business perspective, we are talking about achieving sustainable innovation for the business on the long run. So basically, when we are talking about achieving sustainable innovation, one also needs to talk about innovation maturity. And that's why we bring this up here. And you see those 4 curves there, each representing S curves and the traditional way. And I will talk about this in a bit as well. But first of all, they are representing 4 levels of innovation maturity: product improvement, product redesign, function innovation, and systems innovation. Most companies today are exhibiting only incremental changes in behavior. For them, it takes quite a bit of time to make real changes. In addition, they are still slow in reacting to changing requirements. And we talked about requirements all the time and how we need to be able to react to almost real time, especially when something is on the road. Often the timeline for them is counted in months for those companies where they are today on the incremental changes in behavior, to make use of the data and information and turn this into insights. Today, companies understand that they must go beyond the traditional typical S-curve in order to stay competitive. This moves company to the higher level of product redesign. It was mentioned earlier, this is where most companies operate today. To go beyond that level, companies need to start the journey of digital transformation. And here we are talking right there. You make a decision, you're going to innovate or you die. So that is right there. In order to stay competitive, you need to be able to go through beyond the level of product redesign. To the first stage of transformation, that transformation, companies can achieve functional innovation at that point. Leaders, companies that are able or getting close to innovating at the speed of thought are at the level of systems innovation and lead in their respective industries. This is also the level where a company organization enables cognitive capabilities. And we talked about this. And this way it grants a business coveted ability to reach a new horizon of system innovation. And with that, the viable position to disrupt the market. And look at companies like Tesla. They disrupt the market. Of course, there are a lot of things that they can do better still, and they are aware of that, but they definitely disrupt the market. So let's look here at the typical S-curve. And when you look at the colors, the greener it gets, the better it is. And of course, when it's getting red, you're going down. It's like the S behavior. You decline and you retire. But maturing further requires applying new model-based principles within engineering and to move beyond a company's 4 walls. This is where we have to look how we apply the thinking what we talked about and make use of a product even while it is in service. This is where we are making money today with our new products. And this requires a changing in understanding the way we think about the life cycle. And especially with the enablement of IoT and digital twin, there is additional untapped potential for a product and its related IP while in service. Only mechanical life and user acceptance decide the remaining life of a product at that point. You get software updates over the air nowadays, and you see this with a Tesla all the time. Try to do this, as I mentioned, with a typical car with all the different independent operating systems. That's not going to work. You need a consolidated operating system in order to do so. You need a proper systems modeling and simulation approach. And we talked about this with the various aspects, and I mentioned this in a bit as well. So we talked about process, culture, and maturity, and the importance of the data. Data is the foundation for everything. Without it, systems modeling and simulation will not exist. Where do processes and culture come in? Processes are enabling behavior, and culture defines behavior. In turn, maturity defines the market position. And I'd like to highlight here that technology is not even mentioned. Taking care of organization, culture, and processes is the most important thing. Technology will follow automatically. Before going into the final stretch of our presentation today, let's have a look what it makes maturing towards what it takes maturing towards innovating at the speed of thought. Utilizing the data foundation, we would like to increase the maturity of the organization to achieve systems modeling and simulation capability. By organizing the data, information is created. This enables the behavior of learning over time. This way, it enables the market position of data management leadership. Adding expertise creates intelligence, what in turn enables reasoned thinking. Adding expertise creates insights. This in turn enables predictive ability as behavior and operational management leadership as market position. Vision will allow inspiration, but without action, no innovation is possible. Only at that point, companies are able to lead change and achieve an innovation leadership role on the market. Together with the discussed enabled infrastructural elements, companies can reach the level of innovating at the speed of thought. This is where we can find cognitive behavior. So that is when we are starting to look into the final stretch here. So the next 2-3 minutes, I will talk about what does it take and why we are talking about the power of end-to-end approaches here. So let's talk first about maturing towards higher levels in engineering. And I just talked about maturing towards innovating at the speed of thought in this section. And I'd like here to discuss some specific on how to approach the digital transformation from a system modeling and simulation perspective. In this slide, I have shown the general steps for an engineering-driven organization of how to move towards higher levels of maturity. Traditionally, companies used test-driven development approaches, and Ed was talking before about this. This is followed by the document-based approach. The vast majority of organizations have at least this level of maturity established. Without this, they wouldn't be able to stay in business at all. The question always is, though, how good is their implementation? Still, especially in our day and age, simulation is key to be able to develop new products and services and stay competitive. Model-based development support is essential. Most of the time, those are independent models. Teams are too often still operating in silos. To move towards Mbsc, models need to be integrated. The top level is represented by cognitive principles. This is the level of systems modeling and simulation, also, as mentioned earlier, associated with innovating at the speed of thought. All those stages need to be enabled in the journey of digital transformation for engineering-driven organizations. This is how the engineering maturity in all its facets can be increased. So far, I didn't mention the content underneath the text boxes here. They represent the focus on process-driven foundational elements. Here we can find again some of the key elements that need to be enabled to reach a specific capability and thus system modeling and simulation maturity of an engineering organization. They are all linked one way or the other to system engineering principles, as we mentioned earlier with talking about the engineering beat. All this needs to be balanced using the following main three maturity categories. Ed talked about this: organization, process, and technology. And so what are the essentials to deploy systems modeling and simulation? We need a fundamental understanding, and you see this here with planning, governance, education, execution. We need to form a core team and council, talking about and establishing understand as is and to be. We talked about this, Ed mentioned that, and we are using maturity models for that, which are, in our case, we developed those ourselves using screening assessment, detailed assessment, and follow up, because you cannot just do it one time. You have to go back and verify, did you achieve what you wanted to do? We talked about identifying the gaps. Based on this, we developed solution and associate roadmaps in order to be able to execute, having a path forward and define the specific project, pilot projects. So this is when we talk about, from a modern perspective, how do we help organizations? This is where we are talking end-to-end partnerships ecosystems. And this is where outside help is coming in, consulting, helping to execute, deploy, guide solutions, education and training. It always comes from the outside. Internal organization is very difficult to change behavior. And this also helps to engage properly the solution providers. So this is when we are talking about an end-to-end execution approach through partnership ecosystems. In our case, one of our major partners is Tech, an engineering-based, an India-based company operating out of three major cities of Chennai, Bangalore, and Pune, and of course other areas, but it's an automotive focus. We have another partner from a PLM perspective, US-based SimData. Another Indian partner from a service providing, helping companies, a smart project based out of Bangalore. And for lean manufacturing, lean management in general, for our partners, a US-based company. So a couple slides before wrapping up here. When we are talking with the partnership with Tech, looking at the digital consulting service, and you go through this, what you see here, AI, model-based system engineering, IoT, digital twin, and cognitive behavior, Industry 4.0, cloud and automation, big data and analytics. You can read all the bullets yourself. But what we talk about here is what is highlighted on the bottom here, partnerships with end-to-end delivery management. And this is in order to help the digital transformation as a journey. And this is when we are starting with the discovery to align the business priorities from an outside perspective, and in order to help with data-based decision models. We talked about the data as a foundation. And to wrap this up, let's look at the critical success for digital transformation. Customers realize that investment must be made in an organization, process, and technology. In order to drive an innovation culture, organizational components must be transformed to increase communication and collaboration against typically disparate silos. Education is a cornerstone of this organizational transformation to ensure the rollout is easily understood by all levels, including executives, and especially executives, and we need to keep it simple. The next transformation must be in process. By adopting agile and adaptive methodology and effective governance, a solid data foundation and backbone can be achieved, resulting in effective simulation-driven engineering. The third transformation will be in technology. Artificial intelligence coupled with augmented and virtual reality will help the cognitive abilities needed for future product development. The business results will be reduced time to market, reduced physical prototypes, reduced reworks, increased reliability, lower warranty cost. There are, of course, many more factors involved in a successful digital transformation. This overview is intended to show some of the most critical and important ones. And we hope that we gave you an overview about the complexity when we are talking about positioning, system modeling and simulation as a major part of the digital transformation. With this, I would like to thank you very much, and hopefully we can follow up with you afterwards at any time. Thank you again.
just move forward to take some of the questions from the audience. So here you go. The first question comes from Nitin Negi. Increasing complexity is resulting in more risk and failure. Put some light on it. So this is the question comes. He wants to understand how the situation is putting us into more of complexity because of the enhanced feature and expectation from the consumer also. So can you put some light? How are you dealing with that? How are you helping the companies with that?
Yeah, definitely. As we mentioned throughout this presentation today, complexity is from a demand perspective, from a requirements perspective, and of course, the way the end user wants to use this is how you address this from a company perspective. Developing and maintaining is that you have to have, as we mentioned, a collaborative approach that is not just within the company, but also across the entire supply chain. And when it's on the market, you have to be able to gauge what the feedback is looking like. In order to do so, you have to have common data backbones. You have to have common models available across the various domains. There is no way that you can get away with this, that you have separate what we call silos that have their independent models. Because if you don't bring those together, they develop independent, and then you start, as I mentioned before, in the benefits of the system modeling and simulation, that you increase your cost towards the end, because you realize when you bring the system together, the components together, even in a virtual way, that all of a sudden you have to optimize because something is not working properly. Yeah, and when you look today, as I mentioned as well in the presentation, that there are enough or way too many independent compute units and operating systems today. If this is the case, you always have a certain risk that certain systems are not working properly with each other, and especially with the age of electronics coming in.
I would request you to keep the answers sharp and short so that we can take more questions. So next question comes from Kanan Raghavan. He wants to understand how do we impart system thinking? Any systematic steps to adopt that?
One of the major thing actually is education, in order to make people aware what does it entails. And of course, a presentation, a talk like today helps. But one thing is educate all the levels. And we mentioned in particular management, but at the same time, when we are talking about the practitioner, the entire organization needs to be part of this. In order for them to be part of this, they need to be engaged early on and need to be made aware what does it take in order to do so. If you just say we do it, you don't convince them. So it has to be a coordinated effort and throughout the entire organization.
So I'll take the last question in the interest of time. This one coming from Sunil G. I have been system engineer for electronic system all my life. For complex automotive systems, should I learn about Mbsc? Where should I start from?
When you have been a system engineer for all your life, I think you have a very good basis. You just probably didn't use the term model-based system engineering. Our experience is that those from embedded system software perspective have the best understanding from a system engineering perspective already. What you need to get exposed to is the other areas from a traditional simulation perspective in order to help them to understand what system engineering means in order to lower the hurdles, so that they can communicate as well to you what their needs are in order to create and develop common systems. I think where you are coming from, you have the best basis actually to understand Mbsc relatively easily.
So one final question, how do you see the Indian automotive manufacturing or engineering ecosystem adopt changes that has happened at the global turf and take advantage of that? How do they leverage that? Because there are some constraints that Indian manufacturer or Indian companies have, but if you compare with the developed countries, so how do they make use of the situation or the developments or the progress that developed nation have made in this direction?
Right. One of the things what I see, and I have to even to put this into perspective with the current situation of the pandemic, the transformation, especially the digital transformation, in order to stay competitive, is accelerating. We had it before going, but now it's even more so accelerating. Now, how does the Indian market or the Indian automotive industry comes in here in that case? India, and I mentioned this throughout the presentation as well, made over the last decade and more a huge step forward. Not just in quite a bit areas, you say, okay, emerging country, emerging technology. I don't see it necessarily this way anymore, because you have top-notch engineering capabilities. You bring top-notch cars to the market, and the one big advantage what you have, you do not have those big legacies like the Western countries have. They have to overcome this. They have I have to say, old traditional workforce to deal with. You don't have that in India. A very flexible culture, and you need to make use of this as your advantage. And I think this will happen and actually accelerating. At the moment, there's still a slight downturn, but you will get out of this and actually move faster than the Western country, in my opinion.
Thank you, Frank. Thank you so much for such an elaborate presentation. Hope the audience must have got a lot to learn from, and they will try to implement while they are on job. Thank you so much once again for joining ET Auto Masterclass. Our next session is even exciting, and that session is on application of system engineer and simulation in industry. And this presentation is being done by S.A. Sudarshan, Vice President, EV and E-Mobility Solutions, Ashok Leyland. S.A. Sudarshan has been an entrepreneur and technology innovator, a mechanical engineer by education from IIT Madras and postgraduate from Stanford University. Past experiences of Mr. Sudarshan include developing hermetic compressors, sheet metal engineering, plant and business digitization, system engineering, control engineering, digital twin, and embedded software development tools. He has a very vast understanding and experience of these subcategories in the automotive manufacturing. He is going to give a presentation on application of system engineering and simulation in industry. And also my colleague Shruti will take over, and she will join the Q&A session. Thank you so much, Mr. Sudarshan, for joining ET Auto Masterclass. Over to you.
Thank you, Nabil. Good afternoon, everyone. So continuing from the last question, my presentation will present what is the state of the art as far as this system modeling and simulation, or Mbsc, in Indian automotive industry is. So let me set the context. In a way, it is a repeat of what Frank and Ed talked about in the previous session. So if you look at the current mega trends, one of the main things that is driving is, of course, the climate change. So apart from climate change, you have the next thing, urbanization, and then demographic change. So urbanization refers to more and more people living in cities, increasing the population density, and demographics relates to the age profile of the people living in these areas. In this, India is a little different from rest of the world. So in rest of the world, especially the Western world or Japan, you have the aged people making up a majority of the population, whereas in countries like India, it is less than 30 or 40 years of age making up the majority. And this requires a kind of difference in the way mobility in particular and many other domains need to respond to these. And the last, again, as the previous session explained, digitalization. These four mega trends are kind of demanding rapid innovation. Again, innovation at the speed of thought, or however we want to put it. But in terms of mobility, and of course, the latest mega trend is the coronavirus, COVID-19, or whatever you want to call that. So all of this demand very, very innovative solutions, and more so in the mobility area. And this has led to an acronym. So different people call it different terms, either the way you arrange it. So connected vehicles, autonomous vehicles, shared vehicles, and of course electric vehicles. Or it is also another acronym is MADE, Mobility as a Service, and then autonomous, digital, and electric vehicles. So different acronyms, but end of the day, the result is the same, which is innovation and faster innovation. And when we come to OEMs, what matters? So this is the market capitalization figure for the major global OEMs. As we can see, Tesla has outpaced every other automotive competitor. And actually, if you look at sales-wise, Tesla probably won't even figure anywhere in the top 10 in the world. But despite that, in terms of market capitalization, Tesla is more than twice that of its second place Toyota. So why? Why is this? So it's the readiness for future. Again, as was mentioned in the previous session, Tesla is perceived to be ready for the future. How? In what terms? Let's see. But before that, two slides about Ashok Leyland. So Ashok Leyland too has a number of industry firsts. So starting from way back in 1967, all the way up to the last time the slide was updated, which was about 4 years ago, we have had a number of firsts. And if you see, Ashok Leyland came up with a zero emission electric bus almost 5 years ago. And today, what I'm going to talk is more about how this systems engineering and the simulation was applied in the development of electric bus. But how do we say an organization is ready for the future? So there are three main factors that an auto OEM needs to excel at. The first one is new products and features. And obviously, this is where Tesla scores. And as I just mentioned, at least as far as Indian market is concerned, Ashok Leyland has introduced a number of products for the first time. The second one is manufacturing. This is even more important in India, where quality and cost both are very important, and these are determined by how good an organization is in manufacturing those new products. And finally, the third, when the vehicle is in operation, its reliability and running and service cost. So what is the fuel economy? What is the maintenance cost year on year? These are the three parameters over which any auto OEM is kind of evaluated. And then this, traditionally, the system engineering and simulation was influencing mostly these new products and features. So either in terms of analyzing the requirements and all the way till the design, or for the verification and validation part using simulation and virtual lab, more than testing on the vehicle or in the bench. So that is where it was used. But of late, with IoT and all the telematics, even this has extended into this reliability and operational aspect. And again, this was touched upon in the previous session. So the over-the-air updates or the digital twin collecting data on how a vehicle is being used and predicting what are the kind of forecasting or prognosticating how the issues are going to evolve and act on that. So all that, so now the system engineering and simulation covers these areas, and in the rest of the presentation, I'm going to talk about what Ashok Leyland is doing in these areas and where we lag, or where in some places I would say we are even better than the state of the art and rest of them. So this is the new product development process. So you start from an idea and again you go to concept engineering. But along with concept engineering, you have to take it to the management with a business case. And for that, you need a approximate product cost, development cost, and development timeline. And quite a few iterations happen here. We will cover more how models are used for this in this phase and what kind of models are used. And once a product or a program is approved, we go through the requirement engineering exercise, and from requirement engineering, you go to the functional design, from functional design to the logical design, from the logical design to the physical design, and from there to verification and validation. Now, as we just saw, these are all part of the regular model-based systems engineering or systems engineering as such. And we pretty much follow this flow. And in most of the places, it is models that are used for validating the designs at each of these stages. And that is what leads to a number of reverse loops. So at the time of functional design, you kind of discover some lacuna in the requirement engineering. So you go back and revise the requirements. And it can happen at any point. So even during verification and validation or calibration of the software, you discover that certain requirements cannot be met because of cost targets primarily, or sometimes there are technical infeasibilities as well, which could not be identified early enough in the cycle. So you kind of go through multiple iterations. Systems engineering does reduce those number of iterations, but it's still systems, this model-based systems engineering itself is still not that mature, so you have issues. While it reduces number of iterations, it does not eliminate. But another thing, the iterations happen earlier, so definitely the cost of change is lesser. You don't discover it after building a prototype or after going through a pilot plot. You discover them earlier. The benefit is there, but the iterations are not eliminated. Apart from these, systems engineering also needs to handle three other domains. So one is variant management. So typically automobiles, you build a platform, and on that platform you build a number of models. So that's what makes the entire thing viable financially. So you need to kind of identify all these variants and plan for those variants at all stages. Or you at least need to kind of protect the platform for the variants that you can kind of think or you can estimate that will likely be required in a few years to come. And then change management. So changes happen all the time. It could be either because requirements themselves change, or it could be because of various things. The supplier has come up with a new technology and you want to introduce it, or regulations change, or of course some design infeasibilities are identified. And then with all these changes, you need to manage the configurations. And these changes can happen through the lifetime of the product. So model year to model year, or within a model year, there can be changes in the designs. So you need to keep track so that when the vehicle is to be serviced, you know precisely what version of a particular design or a software is used in that product. So these three also are to be enabled and handled as part of this systems engineering. So now let's look at this concept engineering in more detail. Now there are typically three levels of models that are used for simulation, especially for systems engineering. The first one is known as L0 or level 0, and here the model is more data driven or a black box model. And there's also a concept called a backward model. In a automotive domain, a backward model is you start with a drive cycle. You say the vehicle has to go through this kind of a drive cycle with this kind of a load. So can I estimate what should be my engine torque speed characteristic? Or in case of an electric vehicle, you kind of say what should be the battery size, what should be the motor power rating, or things like that. And for this, you don't really need much of physics. You do need basic physics because from to get from the drive cycle and load to the power, but that is the only level. At this point, it doesn't really matter whether it is an engine or a electric vehicle, because at the end of the day, torque is what that prime mover needs to deliver. So you use these levels of models, and you use these models to do that simple what if analysis. So if I use either this kind of an engine or a combination of motors, what kind of performance can I get? And is it technically feasible? And if I have these kind of cost targets, and if I compromise on this particular aggregate, what is the kind of performance I can expect, whether it be fuel economy or whether it can be the load capacity, payload capacity, or in terms of acceleration or things like that. And you also know what kind of broad aggregates you need. So these are the high cost items. So the emphasis here is on estimating both the development cost as well as the final product cost and the timelines. So how long do we need to develop? When can we use existing aggregates? Where can we use where do we need to use new aggregates? So that means the verification and validation time will increase. So how much of virtual testing, how much of bench testing, how much of on-road trials do I need? So all that will help in doing this. And the issue here is when it comes to autonomous vehicles, of course, we don't have too much direct experience in autonomous vehicles. We do have a few prototypes with level 1 automation, but not much of systems engineering could be used at that point because there are too many unknowns. And that being in lab stage, to a certain extent, you need to rely on a build vehicle. I mean, you need to build a vehicle in order to learn more in terms of what is your performance expectation even. And even in electric vehicle, but as I mentioned, now we have about 5 years of experience in building electric vehicles. So with that, we have a broad understanding of what concept engineering means. And in technology and supplier evaluation is another area, especially in both this autonomous and electric domains. You do a concept engineering, and by the time the business approval comes, by then the technology has evolved. So typically, again, you go back to the drawing board and refine your concept. So through this concept engineering exercise, now we have come to kind of say, these are the kind of parameters that we need to optimize at concept engineering stage as far as the electric vehicle is concerned. So cost, that's the number one for electric vehicles. Next is range. Next is charging time. Again, since Ashok Leyland makes commercial vehicles, these commercial vehicles need to be on the road as much as possible. And for that, obviously, the charging time needs to be as low as possible. So that's a trade-off that we need to do. And then the charging infrastructure as well. So depending on where the bus is going to fly, we need to take into account what is the charging infrastructure available, and depending on that, appropriately design the adopt an appropriate concept for the bus. And of course, safety and the battery life. So these are taken as the parameters that are to be kind of reasonable targets for these need to be fixed at this concept engineering stage, and that is what we use these L0 models to do that for all our variants. Next stage, next step is the requirement engineering. We are assuming that the business case has been found satisfactory and we have the approval to go ahead. And you collect requirements from multiple areas and convert that English to engineering. And traditionally, if you look at our diesel buses or diesel trucks, we don't do a formal requirement engineering. mainly because it is all legacy. There is a lot of knowledge built in, a lot of, pretty much all the design engineers know this is what is required, this is what is not required, and only certain new requirements are kind of passed down. But then we discovered when it comes to electric vehicle, you kind of everything is new. A lot of it is new, so we had to do this as a formal exercise. And here are two diagrams, kind of again these are the systemal language. So use case diagram and state machine diagram. Why do we need this? Because there are stakeholders who are new. So earlier you had for a fueling station, now it is a charging station. And then you have battery recycler. There are different kinds of stakeholders now, and you need to identify how these stakeholders interact with the vehicle. And with that, you need to identify new use cases and new state machines. So what are the different states that the vehicle can be in, and how does it transition from one state to another? So what should it do in each state, what should it not do, all that. So this charging types and situations, then manufacturing considerations. This is again a different thing. Battery needs to be handled somewhat differently. So how do you sequence your manufacturing? So again, manufacturing is a stakeholder. So what are the constraints there? Existing plant, how much modifications? Next comes the parking and the operational scenarios. So with electric vehicles, I mean, diesel vehicle, you can just leave the vehicle, park it, forget it. In case of lockdown like this was a use case that kind of told us that we did well in anticipating this kind of a scenario, where we just had to leave the bus park, and you have to make sure that the battery stays in a very that comfortable window of state of charge. So those kind of use cases, so anytime you work on these new vehicles, you have to spend time identifying these use cases. The other one is emergency responses. So can we use water to put down a fire in case of a battery vehicle? So these are the kind of questions you need to identify, and concept engineering or requirement engineering, you just state them as requirements, but you resolve them as you go on through the RFLP process. Servicing considerations, same, what do we need, what are the constraints, and things like that. And then we go to the functional design. So what main this thing is, this is an intermediate step between the requirement engineering and the regular design process. Typically, most engineers jump from requirements to straight away identifying the aggregates. But this crucial step of functional design is important again for these new vehicles like electric or hybrids or fuel cell vehicles or even autonomous vehicles, because you still need to decompose whatever requirements that have come in terms of functional specifications. So what do we mean by these functional specifications? So here is an example. You can say, let's say you want to design a kind of auto headlamp. So you kind of define that into more functions. So when should the light come on? So when should the light go off? And in this process, there can be a kind of conflicts. And here again, these requirements, even though this looks like English, it is a kind of formal language. And it is using that if light intensity is a variable, is greater than, is greater than, it's a mathematical. So this is a formal language, it looks like English, but the advantage of modeling a requirement or modeling a functional specification in this kind of a language is you can even simulate it. And you can see if my light intensity goes through this kind of a profile through a day or whatever, and this is how my light should behave. So if the functional specification is correct and if the later logical and the physical design are proper, this is how it should behave, and this is what the end user would expect. So you can do a kind of that requirement validation. So all that now is getting into more and more models, and this is what leads to again the next level of systemal diagrams like activity diagram. So as we just saw, these kind of activities should happen, or sequence diagrams. So sequence diagrams are more like timing diagrams. So these become important, especially like in an electric vehicle. Now you have the electric vehicle and it has to communicate with the charger, and there is data communication between the two, and there is a handshake involved. So there are a lot of time constraints. So the vehicle needs to respond within so many milliseconds to what the charger says, and similarly the charger needs to respond within so much time. So that's laying out the sequence diagrams becomes important. And as the number of controllers within the vehicle also increase, already in our traditional diesel vehicle we have about 3 or 4 controllers, but in electric vehicle we already are counting about 8, 9 controllers. So there is a lot of interaction, and the sequence diagram becomes important with all the interdependencies. So we need to specify that upfront, or at least identify that these are the interfaces that are there between the different functions, and you kind of map out the sequences. And the state machine diagram that started out at vehicle level, now it kind of gets decomposed into the functional level. You identify more states at different functions and see how they do. And here again, we go to the next level of models. We still, for most functions, use L0 models, but for some we use L1 models. So typically the state machine diagram can just evolve into a control strategy. So there it's already becoming more detailed. So you have a L1 model, and wherever there are certain you are reusing existing functions, you can just reuse the models themselves, and that is what we do. Next, we go to the logical design. So this is where the actual design, the how part starts. Till this point, we were only describing what should happen and not how should it be implemented. Now more and more engineering analysis comes. So in addition to all that, we get the functional safety requirements, hazard and risk analysis, fault tree analysis, and the failure mode and effect analysis. These add to whatever have come through from the functional specifications, and we do the logical design. So first thing is architecture. So what do we mean by an architecture? There are multiple architectures in the vehicle. The first one is the powertrain architecture. So in case of electric vehicle, we typically evaluate between these different architectures. The first one is, should we use a high energy source and a high power source, or only one? And should we have a DC-DC converter between this and the inverter? And from the inverter, that's the electrical part of the circuit. And from the inverter, should it go to a central motor through a gearbox to the differential, or can we do away with the gearbox and just have the motor drive the differential directly, or can we even go for multiple motors? So 2 or 4 independent motors driving the shaft, or even go for in-wheel motors or hub motors. Today, because of cost reasons, we don't go for multi-motors. We are still with the central motor. But every time we start with a new design, we still do this just to make sure we are not missing an opportunity. So powertrain architecture, again, all this is model based. We have models, pretty much L1 models for everything. So for a particular requirement, you can evaluate what are the trade-offs, cost versus other benefits, and decide, take a decision. Other architectures are like structural architecture. So do you use a ladder frame or a monocop structure? And then the hardware side, I mean high voltage side, you first decide should it be, what voltage should it be? Should we go for something like 700 volts or 350 volts? What are the pros and cons? And what are the low voltage architecture? Should we have how many DC-DC converters do we need? Do we have the each system on the high voltage one or on the low voltage 24 volt system? Then the data architecture. So how many controllers? How should the controllers communicate? How many CAN channels? So those data architectures. Then with electric vehicles, another complication is this thermal management. So you need cooling for multiple systems. So the battery for Indian conditions, it needs a chiller. And then the power electronics and the traction motor, they need their own cooling system. And finally, in case of a bus, the cabin needs air conditioning. So at least on a broad level, there are these 3 cooling systems. But depending on other aggregates, there can be more. So do you go for one central thermal management system, or do we go for multiple thermal managements, or somewhere in between is all possible. So now we use more of L1 and L2 models to take these decisions. And uh, and without these models, I don't think, I mean, any design you do is more a guesswork, and then it will be definitely suboptimal. So at this point is when you start identifying the what are the major blocks, what do they consist of, and how do they talk to each other, and what are the critical parameters for each of those blocks. So you draw the parametric diagram, you draw the block definition diagram, and the internal block diagram. Of course, we don't use the standard SysML, it is too top heavy. So instead, we typically use mostly Simulink and use just build the Simulink models in that. And for some L2 models, you might use a dedicated plant modeling tool. But predominantly, even at this stage, it is all Simulink kind of a tool. And then we go from there to the physical design. So you start with whatever is the output of the logical design, and we start doing the detailed engineering design. So here we cover the mechanical or electrical parts. So this is where the L2 model becomes L3 model. L3 model is still a one-dimensional bulk parameter model. So it's a system model, but more and more we are doing co-simulation, combining that with 3D FEA tools. So that we can analyze how the battery pack goes through the temperature distribution over a drive cycle, or even how the motor behaves under different conditions. And we also go for controls development. So I'll cover the controls development in more detail. And end of physical design is where you have the manufacturable designs. And India traditionally has been very strong in CAE. And with systems engineering coming into the picture, co-simulation is also picking up fairly well. There is a trade-off required here. There is no point in doing co-simulation because it is quite computation intensive for all scenarios. So we use it sparingly or more to gain an understanding, and after that we kind of enhance the L3 model using whatever has been learned, and do most of the optimization using L3 models, and do only a final validation with co-simulation. It requires too many resources, and it takes up too much time. So use it sparingly. So that has been our learning. Then we go for the controls development. So if we look at the controls development process here, again, we have been following the model-based software development process. So whatever requirements that come into subsystem functional specifications, and now from the subsystem, when we identify the controller, we identify those multiple controllers. One level, you have the unit ECU functional specifications. Another is the interface specifications. So from those timing diagrams or the sequence diagrams, you know what are the kind of messages that each ECU needs to exchange with the other with all those timing specifications. And there is interdependency, so there is no point in each ECU evaluating or calculating certain thing. So if one particular ECU is calculating that, then that information is shared to the other ECUs, so they make use of it. So all this, so who is the owner of that information, who are the consumers of that information, all those need to be identified. And at this, for this, we still use predominantly Excel for these specifications. And there is a lot of back and forth as these specifications evolve. And finally, you build the logic. That logic is built in Simulink. And also use those specifications to arrive at test cases. The main advantage with model-based software development is you can do that test-driven development at desktop stage itself. As the specifications mature, build test cases, and those test cases are used to do both unit level validation and ECU level validation and interface tests. And we use MIL, SIL, as well as HIL kind of validation for this. And then we go for a subsystem test. Here, right now, we do not have a HIL system. So for subsystem test, typically we do it on the bench. I will show it's a kind of quasi lab bench, not the vehicle. And finally, you take it for the vehicle. So there is calibration that happens both at the subsystem and also at the vehicle level. And finally, the software is ready for release. So the same thing, look, so again, we use a kind of iterative development. So one particular function or feature is implemented and it pretty much goes through all the entire V&V, and the next feature is added, or that particular feature itself is enhanced in multiple versions. And quite often with a limited functionality, the ECU will be undergoing even vehicle tests. So the change management also becomes important, and as I already said, with the variants and these changes happening, configuration management is also important. Multiple strategies are available. Either you go with the one mega model and switch on the features depending on the product, or in the build process itself you can automate so that the relevant features are picked and relevant versions are picked, and your software is built. And at this point, we follow a combination of the two in the development process. Next, we go to the each software development in more detail. If we look at an individual software development, so we look at the requirements and then come up with the software architecture. So again, software architecture is in terms of how do we represent the functionality. Again, at the individual ECU level, which function owns which signals, and what other signals does it need, and using that architecture come up with the software specification, and that software specification is implemented. And so here it is all happens in Simulink. We are not doing anything in C code, and the model is peer reviewed. And after peer review with traceability to requirements, so all this, we do unit tests, again MIL or SIL, and as we do unit tests, we measure the coverage, and if coverage is not adequate, we need to increase the unit test, so you achieve your targets for the coverage. Then do static tests, typically for on the generated code, do this basic Mbsc checks, and formal verification as well, so that some of the problems that tests cannot identify can be uncovered. And once the model or the software undergoes these steps, we go for the integration test. And even at the level of integration test, so the test cases now can be generated from whatever the formal functional specifications that were designed earlier, and these test cases can be used to automate the tests. So we can arrive at different kinds of all the test cases and do the test automation easily with the integration tests, and do the coverage measurement, and again add more integration tests if the coverage is not adequate. Go for the HIL test and do the calibration and release that can happen on the bench or and in the vehicle, and finally go with the release. So a lot of model-based V&V happens even here. So first one, as I already mentioned, the unit test specifications can be derived from simulation at multiple stages. And the lab vehicle, so this is the kind of lab vehicle where it is a combination of hardware. It is not actual vehicle, but wherever necessary, we have used the low voltage battery and even some DC-DC converters and a kind of driver interface. So you can do testing, and this can even be coupled with today it is not there, but in theory we can couple it with a real-time HIL system. So some plant models can also be there. You don't need, especially for something like high voltage charging, You can't put a battery there, and you can't try to do that. It becomes too expensive. So that you can have a battery model, and the charging cycles can be simulated through that, and see how the overall system behaves. So this is called a virtual iron bird or virtual iron vehicle. We can do plug and play and do the testing. And as I said, apart from that B&B, so that till that point we cover the product development part. Now we move on to the post the vehicle is in operation. What do these connected vehicles or all these telematics enable? So initially the vehicle itself was a connected vehicle, and then with the IoT coming in and the telematics data getting into the cloud, all this enables us to offer a lot of value-added services. But for the purpose of this session, I will focus more on the vehicle health monitoring. The rest are more business options rather than anything to do with systems engineering. So when it comes to vehicle health monitoring, this systems modeling and simulation enables a lot more things. So first one is you can just monitor and you can track how the vehicle is behaving, but you can also do remote diagnostics. If something is first, as you are monitoring, you are generating alerts. When some behavior is abnormal, not something that you have encountered either in various simulations or even in various road trials. So that triggers an alert, and that alert results in makes the engineer kind of diagnose the problem remotely. So here again, a lot of comparison with simulation. We know what the vehicle has gone through, so you can replay that on the model and see what kind of a problem is likely. And in case it is a software change, you can do over-the-air updates, and with that maybe the problem will go away. So this is what the digital twin enables. So you have a version, or you have a copy of the real world vehicle with you, including the real world conditions that the vehicle has gone through, and this also enables prognostics. So now you can kind of say, okay, maybe this vehicle will continue with the same similar loads and similar drive cycles for the next 1 year, 2 year. Now, what kind of problems can I anticipate? So we do this so we can identify, okay, today we do this more for the battery, and we are hoping to extend this for the motor and other power electronic devices. But already from the motor, we are getting insights like this battery is getting stressed more, so we need to do something. So maybe use that vehicle for lesser stressful cycles or schedules, and go on. So this prognostics enables you to kind of work with these vehicles for before it actually fails. So this is the remote monitoring and diagnostics tool. The prognostics is still not online. We do it more like offline. This again is a screenshot taken from a couple of days ago. Our vehicles running in underworld, so we get the location, and you get pretty much the dashboard. You see, so you kind of see, is this kind of current for this voltage for this speed? Is it realistic? If it is not realistic, again, how do we know whether it is realistic or not? Again, from the model, we know whether it is realistic or not. Based on that, the limits are set, and based on that, alerts are generated, and based on the alerts, we kind of take a corrective action. So to conclude, this is the traditional V cycle, but in our practice, we have had a few problems with this. So what are those problems? First one, again, Dilbert, I think, kind of does a lot of this. So the previous session, we saw one joke, this is another joke. So requirements. Coming up with requirements is the hardest part, and it's even more so for an engineer who is actually rearing to build the system rather than spend time wasting finding out what the requirements are. So this is the first learning. So there's a lot of iterations because you keep discovering requirements late in the cycle, but that's something you have to live with. Second is today in our electric vehicle, we are buying most of the electric aggregates. So we are not building them. So to that extent that physical design is more for analysis or more for verification rather than actual design process. But because we are buying and we are skipping the design step, now the iteration comes after you get the aggregate. So the specification flow down kind of doesn't happen this way. You look at what is the aggregate that is available in the market and you kind of say, okay, with this kind of an aggregate, what is the kind of performance I can get? So instead of flow coming from left to right and top to bottom, it in this case kind of goes back. And sometimes it even impacts architecture definition because let us say we decided to go for two motors instead of single motor, but then you discover that that motor is not available or it is not being homologated for India, etc. So then you go back and you even have to revise your architecture, or you even the aggregate testing, unit testing, we still don't have facilities for many testing many of the aggregates. So because of that, the vehicle itself becomes the test bench for that. So at the time of integration, you discover problems, and that requires again redesign, rework. But despite all this, we believe that model-based engineering has been a kind of silver bullet for us, despite all these problems, whatever we have seen. And towards that, what Ashok Leyland has is we have a web application for all these simulation. So all simulation is kind of centralized, and there is a web interface. So as again in the previous session we saw, the silos are broken down. So people use the same models across the organization. Whenever there is a change in either parameters or in the models, the rest of the organization, there is nothing needs to be done. Next time when they run the simulation, they will see some changes. Of course, they can dig through in order to see what the changes are and how it impacts. And that way, there is one single source of truth. And this has avoided a lot of iterations or a lot of miscommunications and all that. So this has been our experience with this model-based systems engineering. And let me close on a lighter note. So model-based systems engineering does not solve all the problems. So whether it be the parking problem or the traffic problem, or even when you have a better solution, unless you evaluate it, just because you are busy with your routine work, you might miss innovation. So innovation at the speed of thought may happen, but unless it is noticed either by management or whoever the powers be, it may not see the light of the day. With that, let me conclude and look forward to any questions. Thank you.
All right. Now it's time to take some questions from our audience. So the first question is from Mr. Sunil G. He is asking, can we reuse the logical design models built for two-wheelers for like cars or trucks or buses?
Yes, see, because that's the beauty of that logical design. Functionality typically is fairly common. And if the model is built in such a way that the parameterization is correct, just by altering the parameters, a bus needs probably a 150 kilowatt or in terms of payload. So for a logical model, it is going to be more at that level. So payload, if it is a parameter, then the drive cycle may be different, but payload is the only thing different. You just run it through, you will get your what is the kind of architecture, what kind of results you are going to get. So that is not going to depend whether it is two-wheeler or four-wheeler. Okay, number of wheels, if that is part of the logical model, that counts, but most often than not, it doesn't matter. The same logical model can be used.
Okay. The next question is from Mr. Aman Goel. He's saying that the range which is given by OEM is not achieved in real world. So what can we change in the simulation methods for the EVs, which can provide us the real world range of an electric vehicle?
Yeah, see, the problem with that is the real world scenarios are so varied. Okay, so there is a AIS standard for determining the range. This was just like in the old days, mileage was at standard 40 kmph standard speed. Similarly, for now for electric vehicles, there is a test that determines the range. So that takes, I mean, for buses, we take it through what is called a Delhi bus driving cycle with a specified chart. We run it and we determine the range. And that doesn't take into account the various aggregates like AC or other loads that will be there in the bus. So in real world, depending on all those aggregates, and ambient temperature is another very important parameter. As I mentioned, the battery requires chilling. So that again depends to a large extent on the ambient temperature. So during summer, it is going to consume a lot of energy to keep the battery at the right temperature. So in summer, with HVAC load and this battery chilling load, the range comes down drastically. Whereas in winter, then things are better, so the range is better. So to a certain extent, again, the market has to evolve, and consumers also need to understand what all implies. And this is one where again this systems engineering and simulation can help. Maybe OEM can give a model or can give access to an online model where the user can play with this is my cycle and this is the kind of temperature where this is the weather in weather pattern in the city where I live. For this, what is the range? And I'm sure the model can predict, and it will be a reasonably good prediction.
All right. So the next question is coming from Mr. Sombya Sarkar. He's saying that considering the current outbreak of coronavirus, what do you see happening in the next 5 years for the system simulations within the automotive space?
Yeah, it is only going to increase. Because see, even with or without corona is adding to the fact that you can't do too much of physical testing. See, most of our engineers now, almost 65% are working from home, and simulation is the only thing that you can do when you are working from home. So already there have been, as I showed, that our always has grown leaps and bounds in the last 4 months. There have been so many more simulations added to it, and so many more engineers are using it. But even apart from that, as the accuracy of simulations improve, it is a much quicker way to get your job done and a cheaper way too. But okay, the cost angle depends a lot on the organizational simulation strategy. But in general, it is a cheaper and faster way to do it. So I see it only increasing.
Okay, so just last question we'll take for this session. This is from Avinash Patil. He is asking how you control the options on the variants in the complex digital simulation.
See, on the plant part, we have not made it too configurable. So on the plant part, it is mostly manual work. To a certain extent, through the Always platform, we expect the user to specify the configuration or specify the model. And I mean, this is still work in progress. It is expected that it will pick up the appropriate subsystem models. And as I said, cost is important, so we don't use commercial tools for all simulations. We have homegrown code, either C code or Python code. So all that makes it not dependent on customization. So you have to write code to do this config variant management. But that's something we have to do. In case of controller, that is where, because it is a Simulink model and Simulink offers multiple options like reference models, and the reference model can be parameter dependent. So using that we can do. So we do that in part, and in some part do more content based, depends on the time and on the priority, urgency. Is it to be reused? Is it a one-time exercise? All that.
All right. Thank you, Mr. Sudarshan, for sharing your insights with us.
Thank you. Thanks, everyone.
Okay, it's time to move on to our next session. Modeling has been used extensively by all automotive companies for deciding on the best strategies to pursue in mitigating the effects of any kind of disruption. In the next session, our expert, Mr. Anirban Mukherjee, will share his insights on the new age simulation modeling and how it could help decision makers in making the most informed decisions. Mr. Mukherjee is an associate partner with Digital Advisory Services of EY, heading the Industry 4.0 practices over the past 25 years in the industry, working with many industrial majors across Asia, Europe, and US. His experience spans across business operations, technology consulting, with his key sector focus on being energy and manufacturing sectors. Mr. Mukherjee, over to you.
I seem to be having a little bit of echo on the line, but thank you for the introduction. Do tell me if there's any disturbance in the line. I'm hoping this is visible to everybody. So just to give a very quick background, I have been involved with the automotive sector now for well over 25 years. In fact, I started my career with the Tatas with their first BS2 engines, and very much at the age, this was in the early 90s, setting up their Tata Cummins plant, and obviously the simulation tools and the modeling tools that we used in those days have come a long way. So what I'm going to talk about is actually about new age simulation, as you see right here in the slide itself. The thing about new age simulation is it has changed quite a bit in terms of the capabilities of the tools that we have available to us today, but also in terms of scope and also in terms of certain techniques, which I'm going to touch upon. So increasingly, as we continue to do modeling and simulation in our engineering jobs day to day, we are finding new tools come in that we had seen in the industry even 5 years back. The ability to do something like predictive maintenance, which is something that, when I talk to engineers who've been in the industry for 25 years, we've been doing it for 25 years, we are talking a very different language in our ability to do certain kinds of predictive modeling, certain kinds of predictive simulation. And this is primarily because of certain digital technologies that enable us today that were not available before. And I think this topic being so vast as it is, I would like to focus my conversation today, based on the guidance, of course, from folks who have organized this seminar, onto the powertrain modeling and simulation. I think that is of particular interest to this community, and we will talk about some of the challenges that we see over there. Coming from EY, of course, one of the first things that we really look at is, of course, the very large industry trends that are driving where we are today in this industry. And of course, it doesn't come as a surprise to all of us that there are industrial headwinds, not just the COVID and the economic downturn associated with it, but the industry has been facing a lot of technological changes too. And some of this might be regarded as opportunities, but definitely during the time of transition, these are definitely difficult periods, right? So I would like to start off with a few of these that you can already see on the slide. One is, of course, the arrival of the electric vehicle itself. Electrification is a big trend across the industry. We are obviously moving away from a stock powertrain technology, which is the internal combustion engine, using fossil fuels more towards electrification for various reasons, not the least being, of course, that it's a much cleaner fuel and it is required by society in general. The electric powertrain with reduced emissions and much higher performance will be a challenge that we will need to look at as an opportunity too. What does this result in? Not just electrification, but there's also been results in faster designs and faster updates coming to market. Of course, this has been driven by not just by what technology has been changing, but also by consumer behavior itself. I think consumers expect far higher level of customization, personalization, which have come to them through various other forms of marketing and social pressures. But the span of a vehicle, as a model, the lifetimes have been shrinking, right? Which results in, of course, launching new products much faster. The NPD lifecycle, new product lifecycle, is obviously a lot shorter. I'm obviously possibly preaching to the choir out here. All of you all understand this, but new product launch costs now need to be really brought within control. We cannot continue to spend as much on a new product launch as we have always done in the past. And these are things that are driving that are really pushing the button around using more simulation and modeling, which is obvious. Lastly, of course, is value engineering. There is a continuous look for value. You want to do things better. There's a continuous aim to optimize to see whether you can take away that other inch of material and still perform equally better. And some of this requires continuous modeling and simulation to see, what can be improved, in what combination can be improved. These are all scenarios. It is very, very difficult to do this kind of engineering and this kind of scenario analysis if you do not have the right tools associated with your engineering product. I think these are the large trends that we see that are actually driving the need for more accurate simulation in this particular industry. Moving over to the next slide, it actually reinforces some of the points, about how some of these lines have been crashing. And some of this is, of course, from global studies, and some of it has been studies that we've done over time. The shrinking time for product life cycles and the faster go-to-market strategies. 71% have a go-to-market timeline of under 2 years right now. These are things that have changed, right? Some of the statistics available to you right here. I'm sure you're familiar with a lot of this. A lot of consultants present these. We do conduct these analysis. I'm sure a lot of industry, industry publications and industry bodies also share some of this. And I'm sure all of you all understand these pressures when it comes to the need for better and better simulation and better and better, modeling techniques. Of course, one thing that I would like to stress upon is that I have, and that is where I think we as consultants bring some of our own perspective, is that we often bring perspectives from across industry. And I have had the pleasure of looking at and actually focusing on modeling and engineering simulation for quite some time. That was an area of focus for me since engineering, when I was a mechanical engineer from IIT Kharagpur, and we were doing modeling way back in the early 90s. We were using tools like, now some of those tools in those days, which were restricted to, research bodies and institutions, are today available as off-the-shelf products, especially customized for very specific industries. And I'm sure you use some of those tools today, and I'm sure some of the speakers will talk about some of those tools, very much in the, in some of the sessions that you're going to have today, I believe in the very next session. Of course, a lot of these, when I talk about simulation, if I were to give a historical perspective, I think there were various models doing analysis and simulation. Not all of it related just to product engineering, but if you were to look at the various brackets of simulation, you would find that there was event simulation. Based on event and activity simulation, you could do process simulation. Based on that, you could do product simulation. Based on product simulation, a larger entity of simulation was called systems modeling simulation, which again, all of these have great history. I mean, system modeling simulation was taught in MIT way back in the 1960s by a professor called J. Forrester. And that itself has evolved to today's very complex dynamic simulation models today. Of course, the latest in the trend is, of course, what we do by non-phenomenological models, as we call it, which is really models that are not based on physics and engineering, but based a lot more on data, wherein you actually feed real-time data into a model. And we also give these names as artificial intelligence, machine learning. But this model kind of develops a model in itself between input parameters and output parameters when fed a humongous amount of data. And some of these can model very complex physics, which are not necessarily governed by very simple laws of physics, which you can actually model. So it's really a combination of all of these modeling techniques that comes into some of the very sophisticated modeling tools that we see today available in the market. Moving on, of course, this has led to something called a digital twin. I will be the first person, I mean, as a consultant who essentially consults in the area of digital technologies. I think this is a very abused word, if I could call it that. It means different things to different people. Of course, digital twin came from some of the very big engineering majors like GE and others. It was used primarily in the, or I would say in the aerospace industry before any other industry, if you were to take a historical perspective. But I do believe the PLM tools that you use in the automotive industry, and I'm talking of the very large PLM majors, product lifecycle management majors who use CAD, CAM, CAE, computer-aided engineering tools, all packaged together in a very nice integrated fashion, including computer-aided manufacturing, where the modeling extends not just to the product, but also how the product will be made. This is also very much integrated. The engineering models associated with the manufacturing process are very tightly linked to the engineering design models themselves. And therefore, we have something which we struggle in industry, which says the bill of the E-bomb to M-bomb kind of integration, which says, when I have an engineering bill of material, how does that translate to a manufacturing bill of material and also a manufacturing recipe, so to speak. So all of this kind of combines together in industry today in what is called a digital twin, right? And it allows you the simulation. And the basic principle of the digital twin comes from certain principles of Industry 4, which say it is not just simulation, but it is also emulation, which means to say that as the process happens, the data that the process produces, or that a piece of equipment produces, in case you're actually designing an internal combustion engine, some of that data needs to feed back into your simulation model. And the model needs to be able to absorb that data and change its model parameters, its constraints, its relationships, its engineering relationships need to better reflect what is being emulated from the real world scenario. And that's what's called digital twin, when there is both a simulation and an emulation process between what is a cyber physical twin, a cyber twin and a physical twin. Of course, I'm sure there's a lot that is spoken in this. A lot of consultants talk to you about this, but we are seeing finally the tools that have come of age where this can be done a lot more effectively. And this is something that everybody in the industry should be looking forward to. The benefits of this have been shown to be huge in certain industries. Of course, the primary industries that have been using this for quite some time have been defense, have been aerospace, have been areas around energy like wind farms and others. But we will talk about how it also impacts clearly the automotive industry. Moving on very quickly, I think I'm going to come to the very specific topic of the powertrain in the automotive industry, and of course the mega trends that are there. We in EY obviously have this approach of looking at what the pressures are on 3 brackets. We call it the now, the next, and the beyond. In fact, COVID is a great example of where we are looking at how operators need to operate now, the immediate, next, and the beyond in terms of whenever there is a disruption. But we are talking about larger disruptions here in terms of powertrain technology and strategy. And of course, you have some things that you need to do immediately in terms of boosting, downsizing, which is turbocharging and supercharging kind of your own internal combustion engines today, low speed torque enhancements and other things more related to your existing engines today, ensuring the pollution control norms that are coming in every day, and various other aspects of it. Then of course the next, which is to do with increasing electrification, and then of course the beyond, which goes into far more efficiencies of how you would use split cycles and heat pumps and all kinds of technologies that might be expected in the future. Of course, I would not be the right person to do crystal ball gazing right now in this forum. I think we have the experts from the industry here, and we also have the experts in my organization that looks very specifically at technologies as they change specifically. Me, as an evangelizer of the tools that you need to use, will talk very specifically about how modeling helps and what it allows you to do today, right? In a summary, the simulation solutions that exist today in the market for powertrain, do cover, of course, the engine and transmission a lot more than the electric powering solutions. However, even I think the powertrain solution, the electric powertrain solutions are coming into the market. But primarily, as you see, you have categories of solutions that already exist for engine and transmission, some categories for control systems and support systems, of course, because there is a lot of electronics that has obviously come into all the controls that you have, all of which deserve a whole level of simulation before they can actually go into a car or into a vehicle. And then, of course, like we said, the electric powering solutions. Touching upon very quickly on the simulation solutions that exist for the engine, I think they fall under these broad categories. There is, of course, in-cylinder simulation, which I've shown a second, which is a very big area of simulation, very specialized tools available. Everything from simulating how the fuel injection is happening, what's happening to the air fuel mixture, how's the combustion happening, what's causing the knocking, what's causing, all of that, the heat transfer, how does it move onto the, how does the cooling fluids move through the cylinder head, all of that can be simulated. And there are fantastic tools available. I don't have the pretty pictures here, but if you were to see some of the 3D simulations and some of the 3D pictures that some of the big vendors show you all, they can be awesomely impressive. I think the important thing is how do you actually be more pragmatic about your choice of tools such that you can use them repeatedly and use them to simulate all the requirements that you would have. The other categories are, of course, exhaust gas after treatment, turbocharging simulations, and thermal load and thermal management simulation. All of these are specific niche solutions available for the automotive industry. As you speak to your vendors, you will find areas where you would get the right fitment of the solution that you would need for your specific purpose. Moving on, of course, the primary solutions that are available for the transmission itself is, of course, the noise, vibration, and the harshness kind of simulation solutions. These are more systemic solutions. They look at the entire system and it's all. The other ones are related to the strength and durability kind of analysis. Again, when you're looking at an entire system, in all, the whole analysis of various interlinkages and the kinematics and the dynamics across the entire system itself is simulated slightly differently from the niche solutions that you saw, which were to do with just the combustion engine itself. Similarly, simulation of gears and shafts and how they do, how they mesh, how the high-point gear works, and how well they're performing, what kind of noises are generated from these. For example, what kind of loads are there, what kind of wear, what kind of friction, what kind of heat generation. All of these can be simulated using very specifically modeled, the ability to have the primitives to be able to model very quickly and to be able to do the scenarios specific to these components is what these packages bring to the table and essentially help accelerate your design process itself. Before I move on, I remember the days when I was in automotive engineering, and the big challenge that we used to face was how much do we invest in, some of these tools which used to be very, very expensive. And I'm sure all of you all grapple with that question. I think there are two things that have changed since those days, honestly. One is, of course, the sophistication of these tools have gone up drastically. And I also think the cost of some of these tools have actually come down. If you were to look at, what has happened over the last 20, 25 years, the tools are a lot less expensive in terms of how many features you get per dollar, right? The other thing, of course, is I remember modeling my entire assembly line, for example. It was a very nice show and tell for every visitor who came to the plant, and I could show him how the J-hooks moved in the assembly line and all of that. But really, these models are very difficult to keep up. The upkeep of model is one of the things you really need to focus on. In those days, there wasn't really the need to upkeep models because we weren't changing things as rapidly. But today, I see the speed at which things change, not just in the product, but also in the process. And these models are becoming not something as a good to have, but something that are becoming absolutely compulsory. And I thought I'd leave that point behind, that there are two real reasons why why we should change our thinking about investing in some of these models. Moving on very quickly, of course, the whole powertrain, the whole electrification, brings its own challenges, and we have noted some of these from some of the discussions and from some of the sources around the industry. 90% of vehicles have have electronics in their powertrain, of course, and that electronics itself needs a lot of simulation. You have what we call hardware in loop kind of simulations that we do, where you first build a model in loop, then you do software in loop. There's a very structured process to how you do the simulation. Of course, with new kinds of electric motors, power electronics, there is new kinds of simulations that you need to do. There are new kinds of problems that you will face. For example, a very interesting thing that happens with powertrains is that now your noise suddenly you suddenly realize that your gears and your transmission is a lot noisier because you don't have the internal combustion engine, which used to be a very noisy bit of your vehicle, and suddenly that's gone. Suddenly a different part is really noisy, and you need to focus on noise on a very different part of your vehicle. So it's very interesting challenges that come as the powertrain, and of course you're getting very specific modeling tools now that come for very specific areas of battery controls and electronics. Of course, now you're getting advanced battery simulation. They are less easily found. Some of it needs to be built with your vendor, maybe. But there is simulation for power electronics, and there are simulation for electrical engineering solutions that are also available in the market. Of course, I wouldn't be vouching for any industry product here. I come here not with a trying to sell a software solution, but a lot of these exist, and I'm sure you are in touch with a lot of vendors, and of course we can always have the conversation, on that, from a very neutral point of view is what I would have that conversation at a future engagement. But I would not like to leave you without showing you the simulation solutions, the broad categories that you need to look at. Like I say, I come from an environment where I apply simulation and modeling not just to engineering products, but a lot to processes. And that's where I see a huge amount of simulation and modeling that is going in today. And the solutions are enormous, right from what's called an APC, an advanced process controller, which controls, let's say, everything from a nuclear power plant to a petrochemical plant, the process as it happens. And these simulations are very, very complex. You have simulations around planning and execution. In your SAP or your ERP, you have MRP2 simulations that are running. And these simulations themselves are changing because they are now absorbing data. Initially, we used to have a very streamlined process with activities and a certain timeline associated with activity. These are becoming extremely dynamic. Supply chain planning and simulation is a simulation tool. And these follow the same principles of model dynamics, and so what you see on the left-hand side is in the automotive sector, we see planning and execution, industrial engineering, manufacturing operations also use simulation tools, which increasingly need to integrate with the engineering and testing, so to speak, simulation tools. And of course, the areas over here we are quite familiar with as engineering experts, R&D experts, and new product development people. They could be with vehicle dynamics, cabin comfort, electrical drive, electric drive, which is coming in. Of course, the chassis, suspension, powertrain, crashworthiness, brake system engineering. In fact, some of these have far more advanced simulation tools, which include human-in-loop simulation, which you are aware of. When it comes to crash test and brake simulation, of course, crashworthiness simulation is done by very specific organizations with dummies. But brake system engineering and other things are things that definitely have, where you actually have a human testing out braking systems with software models, even when it is at the phase of, a modeling simulation, you actually have hardware, which you can see is feedback from software tools, from software models, and you do what is known as human in loop as part of the hardware in loop simulation. Plenty of other vehicle engineering and testing solutions, all of which you must be aware of. There is acoustic simulation, which is a whole area of specialization. Fluid dynamic simulation, which is another different area. Structural and thermal simulation. Similarly, specific to tires, specific to materials, specific to motion. Body simulation, which comes to meshing to see how airflow happens over, the body that you've designed. Are of course different areas of simulation that you're well aware of. Broadly categorized, what you see on the left-hand system, they are either integrated systems, thermal, multi-body mechanics, propulsion systems, or fluid systems. I mean, that pretty much covers the various simulation solutions that are available in the industry today. And I would just like to jump on to a very quick topic on something else that is of interest to people who are in new product development and obviously R&D. And that is this new age technology of 3D printing. I wouldn't say 3D printing has come of age, but it definitely is something that the automotive industry is looking at. I'm sure plenty of you are also looking at how this can help you with prototype building, with the help of conceptualizing something in 3 dimensions, looking at models that you have modeled in 3D and actually generating a model, not necessarily a functional model, but even something for look and feel and for collaborating with other designers who are more in the aesthetics of it. Of course, prototype validation. Customized parts is something that we are seeing increasingly catch up across the industry. Some parts, including some spare parts that are not necessarily restricted by the type of material that they are built with, and especially this comes to plastics and other kind of materials. We have seen everybody from Daimler, I think, with nearly 20 to 30 parts, right from cable ties to hoses and other things, where parts are also being 3D printed, and of course pre-production sampling and tooling. There is a lot of 3D printing software in the industry, like the big names, some of which are mentioned below. But of course, this is becoming something that is very much a tool of people who are in the R&D and who are in the new product development lifecycle phase. Like I said, it is already getting into action. There are companies in India and there are companies around the globe who are already using 3D printing. So I wouldn't say that this is something very far off. This is something that is increasingly an important part of your portfolio, and would be happy to talk about it a lot more. The costs of this is coming down drastically. It's a very, very rapidly changing field, and I'm sure we will see a lot of exciting time ahead of us, where this combines with modeling and simulation to let you to empower you all of y'all a lot more. Of course, lastly, I would like to leave behind, and this is the very last slide that I'm showing you. Like I said, I don't have a lot of pretty pictures which, let's say, a Siemens or a PTC or a Delmia will come and show you as part of their product in terms of simulation, because I'm not showing you those great simulation 3D pictures. But here's something that's very interesting. I don't know how many of you from the automotive industry would recognize what this is, but this was touted as Silicon Valley versus Detroit, right? This is the new age of making the automotive vehicle. And this is from a vehicle manufacturer. It's not a mass manufacturer of vehicles. It's from Local Motors, who are based out of Arizona, and they took up a challenge. And this is Local Motors produced Rally Fighter in 18 months. It's a vehicle built from scratch in 18 months. We talked about crashing new product lifecycle, new product development lifecycle, right? What you're seeing on the left-hand side is an entirely 3D printed body, that they are. A very interesting phenomenon. This is still touted as a case study in this industry. It's not something that is going to change your model today, but it's something coming down the line, right? So this vehicle was built by crowdsourcing its design. There were more than 150 to 200 designers whose design features were taken in. It is built in a micro factory, no larger than a medium-sized mall in Gurgaon, maybe 50,000 square feet. That's the size of the factory where it gets made. It's just a whole new way of doing things that has been shown to be successful. These cars are not less. I mean they are pretty expensive. They are looking at building now less expensive models, but they're never going to be a mass manufacturer. We're not talking of this competing against a Tata or a Mahindra in India, or against a Ford and a Chrysler and a VW or a Toyota. But it's a new way of doing things where the design and the new product development life cycle has absolutely been crashed. With that thought, I'd like to end my presentation, and I'd like to open up for any questions or discussions.
Thank you, Mr. Anirban, for such an informative presentation. We will now move on to the question answer round. So the first question is from Shreyas Jha. And the question is, with the increased requirement of computational resources for simulations, how are simulations moving online?
Sorry, so could you just repeat that question? So for competing resources for simulation, can we move simulations online? I think is the question. Is that accurate?
Yeah, correct, Mr.
Okay, that's a fascinating question. So I do agree that some simulations, especially the new kinds of simulation I talked about, where simulation is based on a lot of data, right? And this is where I'm talking about non-phenomenological models. I mean, I have an engineering model which I could, in the past, simulate using a rather powerful simulation engine. I still remember we used to have a CAD/CAM lab at IIT Kharagpur, where the most expensive computers used to be thankfully brought for us, and these were really powerful, the most powerful machines that we had in the campus. Today, I think even those machines fall short in terms of being able to do simulation with the humongous volumes of data that are coming out of a test cell, let us say, that you would have for your combustion engine. However, the good story today is that you have data and the ability to crunch data, and the ability, and by that I mean virtual machines that are available on the cloud, right? These are available from obviously the very large cloud providers. You have the likes of the Amazons and I won't name too many of them, but whether it's Azure from Microsoft, or whether it's Amazon AWS, or whether it's IBM's cloud and various other vendors. They do give you the very standard VMs, and by standard VMs I mean that these are machines that are as good as a Unix machine, or as good as a even a Microsoft Windows machine is something that you can have available as a VM. So you can definitely launch your software there if it were a software that you have in-house. Also, some of your providers. So if you were talking to a design company today, or a design PLM software provider, they would also provide you some of these software licenses that are available and these software features that are available on the cloud itself. And so therefore, it would not have to compete with resources in-house. You would not have to look for a huge cluster that you have in your data center to be able to crunch all that data. You could actually use some of the resources available in the cloud. And the good part of it is simulation is usually a very what is called a seasonal activity. You don't necessarily do it all through the year, and it doesn't necessarily need to level out. So it's obviously very good to use the cloud because you can spin off a virtual machine and then spin down a virtual machine, and you don't need to necessarily pay for it. So yes, that's definitely an area that you definitely need to look at.
Moving on to the next question. The next question is from Prashasti. The question is, when we talk about the new age simulation, what will be the ideal balance between physical testing and simulation?
A very I think this question doesn't deserve. I mean, it's such a loaded question that it doesn't deserve a point blank answer. If I gave it to you, I would not be fair to you. I would not be fair to all designers around the country, around the world. I think this is a very conscious decision that all of you all take. But increasingly, the tools are getting sophisticated where physical simulation. So I have ridden in a truck wearing a helmet around the test track of in Jamshedpur of Tata Motors, right? So I think those were the days when that was simulation. You bounced around a test track for half an hour, came out and looked at how it performed, and that was the best you could do. The world has moved on from there, and increasingly the world is moving on from there. So increasingly you will have better and better simulation tools which can be trusted to take your testing and simulation further and further down the track. I don't think there will ever be a day when you will not have physical testing and simulation. I think increasingly, the very interesting thing is, especially in the automotive industry, you are having simulators, right? And if anybody has played Microsoft's recently launched Flight Simulator, you will realize how advanced it is, right? We are getting simulators where the entire vehicle and the vehicle, the feeling of what it would feel, the drivability of a vehicle is also being simulated using software, right? So definitely there is this interplay between human and loop, and how soon you can bring the human to interact with software models. And I have a whole set of discussions around that. But the answer to it, very simply, is that the trade-off is moving increasingly of having more and more software, and more of it is becoming possible, less of it for the human, especially because the cost and the danger and some of that can obviously be reduced. And that would be my answer. I don't know if I've given you a complete answer. I don't think I could say it's an 80-20 or a 70-30 because that wouldn't be fair. It would depend so much on what kind of simulation we're talking about.
All right. We will take the last question of this session, which is from Ramesha. And the question is, does the cost of production increase due to system engineering implementation in product development? If yes, then by what percentage? Mr. Ingrid, can you throw some light on this?
Sorry. So the question again is, how much has the cost increased due to system integration?
System engineering implementation in the product development. If yes, then by what percentage?
No, so it's difficult for me to put a finger to that, off the cuff. I mean, I wouldn't, again, these are things that we can definitely get back to you on. I mean, if you were to contact us, but we do have enough research to back up specific areas of, cost in the whole NPD cycle. The new product development life cycle is something which is a pretty specific area of research. However, the whole point of this particular session is the fact that actually it is bringing down these costs that are possible with simulation. And so I would say there is a trade-off where you need to invest in tools, for simulation and modeling that actually bring down very specifically systems engineering costs itself. So, we would do systems engineering using pretty basic tools at one point of time. If I were to say, the MATLAB tools with Simulink and other things, we do systems engineering, right? However, the tools have, far more industry-specific tools are today available, which allow you to take systems engineering a lot further. These tools actually bring down the cost, the overall cost of systems engineering over the long run. And if I were to say, actually, I would say that a lot of systems engineering costs can be brought down using the right set of tools. And that's where your whole focus needs to be. Because systems engineering isn't going away. With more and more product launches, more and more changes in technology, more and more regulations coming in, you would have to continue doing a lot of systems engineering over and over and over again. So having the right tools will actually bring down your total cost of systems engineering over time. And the right investments need to be made in the right tools at this point of time is where I would leave you at. I don't think necessarily the cost has a very fixed number. It has been going up of late because obviously the number of changes has been going up and we do not necessarily have the right tools in our industry today, and we need to adopt them. Is I think where I would leave you.
Okay, with this, we have approached the end of this session. Thank you, Mr. Anirban, for sharing your valuable insights with ET Auto Masterclass.
Thank you.
Our next expert is Mr. Thomas Debras, who will share his insights on the effective deployment of simulation to engineering teams to accelerate, optimize, and secure design. For the last 5 years, Mr. Debras has managed the 1D application engineering team in France with specific focus on automotive market. Mr. Debras, over to you.
Okay, so thank you to all the previous presenters, because I think many of the topics that they covered will be partially answered by the technical solution that I'm going to share as soon as I will be able to move this. Yes, perfect. This window. Today we're going to talk about how we can effectively deploy simulation to engineering teams to accelerate and optimize and also secure design, because it's one of the challenges. But many of my predecessors talked about the states of the industry, and especially in the automotive industry. And I want to start with some. This is an actual study of the projection in terms of CO2 emission for the fleet of vehicles that will be produced by some of the major OEMs in Europe. And you know that there are some stringent regulation about CO2 emission in Europe, and they will come with, let's say, fines. And this report is very interesting because it's balancing the fine that the OEMs are facing with their annual EBIT, the total income, the total yearly income. And if you look at it, you can see that some of them, like GLR, for instance, are facing fines that are 4 times the annual EBIT. It means that they might run out of business if they don't do something very quickly. Of course, due to the COVID situation, probably this fine will be postponed, and that's a good news for those OEMs, but they are not relying on that, and they have all decided to have some, let's say, disruptive and ambitious plan to reduce the CO2 emission. And if you look at what are the projections they want to achieve since 2025, we are talking about a reduction, a mean reduction of 1/3 of the total emission of their fleet. So you are not going to achieve that if you do not deploy system simulation, if you do not disrupt the way you are designing your systems, your car, or your vehicles. And that's exactly what was exposed by the previous speakers. And let's look at it under maybe a slightly different perspective. What is design? What is optimizing design? Design is just balancing conflicting requirements. You want to achieve the best balance between things that are requiring different qualities to the product that you are designing. For instance, if we take a case of an hybrid vehicle, you want to balance range and performance. Yes, you can have, or for an electric vehicle, you can have a big battery, you will have a very big range, but in this case, the vehicle might be heavy, and in terms of acceleration, this is something that you will pay. So you have to find a good balance between those two requirements. And if designing a vehicle would be so simple, everybody will do it, but there are many other attributes or requirements like thermal comfort, like drivability, and every time you are doing one of those compromise, the global compromise that you can see on the right is decreasing, because there is no way that adding some constraint will improve the choices that you have done previously. And at one point, you will face some pretty specific requirements, like emission, that are not only marketing requirement, but are mandatory requirement, because if you don't comply with the emission, you got the fine I was talking about just earlier. So in this case, if you do not find a compromise that is satisfying this requirement, well, you might have to start your design all over again. And some other type of attributes like thermal safety, well, are also mandatory, because you will not sell a car that is burning in the streets. There is no way you will not get out of business with this kind of strategy. But if we look at the process of designing, you had a very big design space. And in fact, you explored with this sequential design. This is what we call sequential design. You explored only the lines, and the design space was the entire hexagon. So if you go for sequential design, and if you don't go for parallel design or for integrated design, you will not be able to explore the complete design space. And if you make your design team in order to explore the complete design space, you might find some solutions, some designs that were not considered earlier that provides a better overall rating. So this is with integrated design that you will be able to reveal the true potential of a given architecture. Of course, if you want to be able to do that, well, and if you want to be able to change the design when it's still time to do it, you need to have models that you can use as soon as possible in the design cycle. Because you will not do that with prototype. When you have a prototype, most of the time, it's too late to change the complete system design. When you have a CAD, it's also too late. So you need to be able to work earlier and to evaluate the design that you are working on earlier. And for that, I try to group requirements with some types of family, and it's also usually the type of department that you find at OEMs or at big suppliers. But if we look at the vehicle technical definition, there are many subsystems. So for an hybrid vehicle, again, battery, electric machine, engine, after treatments, cabin, etc. You name it. I try to gather here the most representative and the more important subsystem. And if you want to be able to assess range and performance, first, for the battery, an equivalent circuit model could be good enough. Map-based model for engine and motor could be good enough. And of course, you don't need to model the suspension when it comes to just pure range and performance analysis. But people from the drivability and vehicle dynamic department will have different needs. And they will use different type of model, and probably the impact of the thermal modeling of the cabin is absolutely there is absolutely no impact on the drivability and the vehicle dynamics, so no need to model this. And we can go on and on with thermal comfort and thermal safety, with emissions. This is the type of model. This is what is happening on what is required for emission and NVH modeling, at least at the first and second level of model. Well, if you want to deploy this methodology, you need to have tools to support this modeling strategy. And let's look at what we have inside our solution called SimCenter AmSim, because I'm not sure that everybody knows about it, because in the previous presentation, I heard that some of this type of modeling were not available. Well, I think they are, and they are in complete integrated way. It means that this is what we can offer for each type of subsystem, and of course what we can combine. And here I decided to split the level of model in 3, but in fact there are much more in some cases, there are less in others, but it's just for you to understand how we can structure the modeling offer that we have in SimCenter AmSim. But being part of a big company like Siemens bring the not only one tool but many tools. And of course, we can do a lot of things with system simulation and 1D modeling, but there is a time where you need to connect and rely on 3D simulation. And with the SimCenter, the global SimCenter portfolio, in fact, we are the only one to be able to provide all the type of modeling tools, whether it's for CFD, 3D, whether it's for analytical battery design, analytical electric machine design. And because we have not only the 1D tool and the 3D tool, we also have all the connection that you can imagine between all those tools. So the next question is, okay, you can provide me with level 4 model and combine everything and have a very good model that is very detailed. Why don't I use only this one? Well, there is a simple reason, because there is no such a thing as free lunch. Yes, accuracy will increase, but also the level of data that you will need to provide to your modeling, to your models will also increase. So maybe you don't have all the information that you need to deal with a detailed model, with a 3D model at the beginning of the design cycle. Well, simply because you don't have a CAD and you want to be able to start working even before you had a CAD. And another key aspect is the response time. If you consider response time between the design question and the time where you are saying yes, it's a go or it's a no-go, this is a response time. You will have creation of model, parametrization of model, and we mentioned that it might require a lot of data, computation of model, and analysis of model. And of course, response time will increase with the complexity of model. So that said, just to show you a quick overview of what can be achieved with a simple model. So this is a range and performance model in AmSim that has been generated literally in minutes, and you will get a decent prediction of CO2 emission, of fuel consumption, of range of maximum speed, etc. Same type of model. We replaced, you can see that here, well, it's a little bit small, but it's not the point of going into too much detail of models. Here we replaced this very simple model of the vehicle by a more detailed model of vehicle for drivability. Now we are reaching this 2D world to have longitudinal comfort. And of course, the same type of model and structure can be used for thermal comfort analysis, for thermal safety. And if we replace, in this case, not the vehicle, but here that the engine that is much more detailed. And you mentioned a tool for detail in-cylinder and engine modeling. This is where you can connect them, or you can use our detailed models for engine. Here, you will have more detailed information about emissions. But yeah, the picture might seem to be too good to be true. So I will just share with you a small video of how to create a realistic dynamic model very quickly. We are going to create a virtual Tesla S and validate it. The video is 5 minutes long. I will give you some comments, but just so you know, it's usually a demo that we are doing and that we have accelerated. The original demo takes, let's say, 10 to 12 minutes. So when I'm saying it's very fast, it's very fast. So first thing that we are going to do, exactly like for a real project, we are going to gather all the necessary data. And in this case, I will start with Wikipedia and get some internet data and put them into an Excel sheet where I can start. Basically, it's a first level of design. Then I will use HOT, the hybrid optimization tool, to quickly select the type of architecture I want to deal with. So you have hybrid architecture, series, parallel, single electric drive, dual electric drive, of course, conventional. And once you have selected this, you will be able to start modeling. And if the data are not in the right format, in AmSim we have tools like the one that you just seen that can translate the data from one word to another. Here we are parameterizing the transmission ratio. Well, for the electric machine, we don't have power losses map. Well, in this case, we will rely on other tools that are embedded in AmSim to get a first assumption. If you have a more detailed power losses, if you want to connect with other tools, of course, you can import at this stage with no difficulties. For the battery, well, we will use what we know. We know the structure of the battery. We know the rated capacity. And for the OCV curve, well, again, we have not much information. Let's use as first assumption a constant OCV curve of 3.6 volts from 0 to 100% of state of charge. You can, of course, select whatever driving cycle you want from predefined driving cycle or import your own driving cycle. Here, computation is done real time. I stopped accelerating the video just to show you, yeah, it's been computed in 1.5 seconds. And with that, I have a first evaluation of maximum acceleration, and so 0 to 100 km/h, maximum speed, and the range. So you see that the range is good, but not excellent in terms of predictability, probably because of the OCV curve that is a little light. What we have done here is a very simple model, and what we want to go, where we want to go is a dynamic model. And here I just hit on the generate button, and without touching the mouse, this is a complete automated process. The model is built by the software, so you don't have to build the model. And then the only thing you have to do at this stage is to perform a new simulation with a dynamic model on which you can change whatever you want. And by the way, you have an optimized controller, the ECMS, that is definitely not the final controller that you are going to use, but that is a good starting point. Here, you can structure the results using post-processing values, and I encourage people to do that and to reuse post-processing value from model to model, because probably you're always looking at the same thing. And here you see we still have this range gap of, let's say, something like 10%. So I don't think that it's acceptable even for this type of modeling. So let's see if we can do something better. When it comes to acceleration, everything is good. So this is another integrated tool in AmSim called the battery precising tool, where you are going to put some macroscopic parameters, and it will generate good enough OCV curve. Of course, we will be able in later stage to increase the accuracy of this model using HPPC test import, this kind of thing. But you saw that now the range is exactly the same. We got a little bit lucky on this. A 1% gap would have been very good, but on this case we are very lucky. We have exactly the same value. Another interesting post-processing is what I'm doing here is rating. If I want to come back to marketing requirements, I can say, well, if I have 500 km of 350 km of range, it's a rating of 0. 550, it's a rating of 5. And now I have in one spider chart a global vision of the quality of my design. So again, here we are talking real time is 10 minutes for creating the model from scratch. And so it's something that can be done by, once is enough, I will move to the next slide. This is something that can be created by advanced research department and also program departments. It can be done by experts or non-experts. But let's look at the workflow. Let's say if we want to add a 2-speed gearbox to this Tesla S, what we would do is we would create the model with hot, like we have done. We will create some post-processing like I showed you. And then this is where it can be a little bit different, but this would take much more time. What we could do is use the integrated DOE tool to explore the impact of ratios for first and second gear, battery size, weight reduction, these kind of things. And using neural network and genetic optimization, we can create automated optimization of the design. So we get some design parameters that provides better ratings. And of course, at the end of this optimization process, there is still a need for an engineer, because we will never replace the engineer. We are just providing the tool to make the engineer more effective. And the engineer will be able to analyze deeply the optimized design and maybe fine tune it. And this is in a world where everybody knows how to deal with modeling tools, but we want to project in the next world where modeling tools are moving to the design department and not remain to specialists. So, well, we offer tools to deploy this kind of methodology. So the main question is, why is there a need to deploy this kind of methodology? Let's look at what happens if the simulation is widely deployed in vehicle design. For instance, we have a new BEV project. So the vehicle program is providing requirement to all the engineering department. You might have a different structure, but basically you will find the same function. At one point, this department will say, hey, we have CAE departments, whether they are dedicated or they have a CAE expert in the engineering departments, it makes no difference, but usually there are people that are dedicated to CAE. What can you do for me? Well, because they have been listening to my presentation and they have deployed this kind of tool, they say, okay, no problem, for range and performance, this is what we can do. Okay, let's do that. But you will not create a model if you don't have a technical definition of the vehicle, because it's not about creating a model, it's about providing answer for the design team on a specific design. So the CAE department guys will have to gather all the information like I did on Wikipedia, and inside the company we know that it can be a little bit challenging because sometimes it's requirement, sometimes it's already started design. Anyway, they manage to do it, they get their technical definition and they provide good intels to the performance department and the energy efficiency department. Of course, if this is done once, everybody will hear about it and the word is spread and everybody will ask something different to the CAE department. And because they are very competent in your company, they are able to provide good information using the right level of model. So this is very good news. We never achieved such a good design for this BEV project. And that was very challenging for the CAE department, but they managed to do it. But let's face reality. What happens if the simulation is really widely deployed in the vehicle design? Well, in fact, an OEM is not working only on one BEV project. There are different programs. For instance, a fuel cell project, an hybrid P2 project, a conventional ICE project. And for all of these projects, there are many variants because you don't create only a platform to create one vehicle, but for multiple vehicles. At the end of the day, this is what happens all the time. The CAE department are undersized considering what they could bring to the company if they can answer to every question that the vehicle program should ask them. So what we think at Siemens is that CAE department should provide method and tools so the engineering department can gain autonomy in dealing with what we call the daily simulation. And the CAE department should stop trying to provide all the simulation to everyone in the company and focus on the most critical one, on the next generation of simulation, while controlling tools that are providing to the engineering department for the daily simulation. So this brings us to, let's say, the pyramid of expertise in terms of modeling that you see at every company, not only OEMs or automotive supplier, but you see that in every company for every type of industry. you have a few expert engineers that knows how to develop and validate modeling strategies that could even do our job, create the software. But those are very rare resources that you need to use in the most effective way possible. You have CA engineers that knows how to develop and exploit digital twins, I mean models, sometimes just following the methodologies that has been developed by the experts. And you have the project and vehicle teams that are using simulation information to optimize the design. Well, in fact, the ones that are creating value in the company are the project and vehicle teams. All the other are support people that will help project and vehicle teams to create more value. And the goal here is to make simulation accessible to design team by spreading the knowledge from the expert to the project engineers. So let's go back to the model. Each department has specific need. This is another view of the matrix slide. You see for range and performance, you will use one type of model. For a fast charge model for an electric vehicle, you will use a completely different type of model. But at the end of the day, they are all working on the same technical definition. They should at least work on the same technical definition. And what will happen in terms of range and performance if people from the battery say, well, I need a bigger radiator because I will not be able to ensure fast charge? Well, of course, this will have an impact on the weight of the vehicle and, of course, on the aerodynamic drag. So it will have an impact on range and performance. So what if, instead of focusing on models, we focus on design question? And that's exactly what we are trying to provide with a tool called System Analysts. And here you see everybody is sharing the same, so this is for a pure EV vehicle, the same subsystems, but everyone has different questions, design question, and we are focusing on this. At this stage is the focus need to be put not only on models and need to be taken out of models to be put on design questions. So we are not talking about modeling to modeling experts, but talking to design experts. Okay. Well, if you look at the process to deploy models, usually you will have one question is, how do I deploy many models? In fact, if you already have done some work creating models, you probably have a database of models that you don't even, you are not even aware of this database. If we worked on this BV project, well, for each subsystem we have we had to create the level 1, 2, and 3 of model for battery, electric machine, etc., etc. And in the meantime, if there is a P2 architecture project, well, you will have to create the engine and after treatment model, and you will have to create the fuel cell model if you are working on a fuel cell model. And at the end of the day, what you have is a component database on one side and an architecture database on the other side. And how do I deploy this model to non-experts? How do I spread this knowledge inside my company? Well, that's where System Analyst is useful. It will analyze, if you have structured your model correctly, of course, it will analyze those model of architecture and component and will bring them into a database that will be able to be deployed to a bigger audience, and people will use simulation without having knowledge of simulation, and very important, under the control of the experts. Because with this workflow, people that are deploying models are responsible of these models, so they know what they are sharing, they know what are the limits of their model, what is the purpose of the model, and this is something that is managed by design in the tool chain. So let's look a little bit at how the final user could benefit from this type of software and simulation deployment. This is the GUI of the system analyst. First thing is finding the right architecture into the database. So we have tool to filter, because here it's a demo database. People that have deployed this tool have hundreds or thousands of models. Then you simply select the type of transmission that you want to use into the database, or you can customize it as a user by changing some parameters. But here you see we don't have to change any model. You can combine whatever model with whatever model. Here we had technical definition of conventional engine, conventional vehicle with hybrid vehicle into the same project. And we had something for performance with something for range. You could add drivability, you could add thermal management. So you can mix everything. When it comes to parameter study, it's very easy to cross in some kind of matrix. Well, I will test this different gearbox on all those different technical definitions. And if you want to test different, I don't know, batteries on an hybrid, an electric and a conventional vehicle, of course, the conventional will be excluded from the generated DOE, because there is no such thing as a big battery. And of course, you will be able to have this kind of ratings and spider chart to do the same type of analysis that I was doing as an expert in AMSIM. You will be able to do as a designer into system analyst. Now, what is a workflow when you deploy this kind of tool, and how does it fit into the company, and how people are interacting through the software? So you see here we have the engineering departments that will mainly work with system analysts, and we have the CAE department that will work with system analysts, so the deployment tool, and also all the authoring tool. Of course, I put the screenshot of AMSIM here because this is the only one I'm allowed to put, but could be some other tools, especially for control, because AMSIM is the reference tool for physical modeling simulation, but we all know that Simulink is the reference tool, and is a de facto reference tool for control simulation, and it can be also integrated into this process. But it will all start all the time with a design question coming from the engineering department. So am I able to evaluate this attribute for this given architecture? I don't know. Can I do some drivability analysis on a P2 architecture? Well, this is something that the final user will look through the GUI of the tool with the filtering feature that I was showing earlier, and it will silently explore the model database and provide an answer. So let's assume that we are lucky. Well, yes. Okay, so next step, I will get this technical definition available for me. Next step is I need to parameterize all the components, the electric machine, the engine, the transmission, well, the gearbox, the vehicle itself. Are all those parameters available? Then at this stage, I will still use the same GUI and look into the product database. And here we have a different database with product informations. So I'm not talking about PLM, I'm not talking about the information of your own product, but of all the potential subsystems that you can use. So you will have all your battery suppliers definition, for instance. Well, again, we are lucky. Well, you can create the simulation and perform it and use it to improve your design. Here, this workflow, if the answer is yes, we're talking about minutes between the moment where somebody in the engineering department has a question and the moment where he has the answer. Well, let's assume that we are not that lucky and the parameterization is not available. In this case, the final user, through the GUI that I was showing earlier in the video, will be able to create his own parameterization and share it with his colleague, because it's all handled in revision, it's all handled with right management, and it will be able to publish the parameterization or to keep it for himself if he wants. Once he's done that, of course, the product database is enlarged and improved, and he will be able to perform the simulation. In this case, we are talking about a complete workflow in less than, I'd say, half an hour, something like that, depending on how much parameterization the user has to do. And in fact, what will be the critical point in the timeline is, does the user have all the information that he needs? This is always the most challenging point. Now, we are not lucky, and in the database of model, there is no such an architecture. So now the question and the ball is going to the CAE department, and then there is another question. If I want to create this architecture, for instance, I don't know, I want to create a battery electric vehicle, and I already have a fuel cell vehicle in my database. Well, probably a battery vehicle is just a fuel cell vehicle without the fuel cell. So probably I have all the component models available. So what I need to create is only, so of course I will check into the model database, and what I will have to create is only the architecture model, and then I will publish it. And the CAE department is in charge of providing tools, providing the first simulation. He's not in charge even of optimizing the design. So he will say, okay, I published this new architecture. Please, engineering department guys, take over from here and do the parameterization and perform your simulation. And if you have some trouble, come back to me and we will look at it. And now there is a last case with that where we are missing some component. Let's take the other the example the other way around. You have already published a battery electric vehicle architecture, and you want to work with a fuel cell vehicle. Well, what you are missing in this case probably is the fuel cell model itself. So you need to add this fuel cell model, publish it in the database, then create the architecture combining fuel cell and battery, publish it again, and people from the engineering department will be able to fine-tune the design, make what-if analysis, compare fuel cell with pure BEV, with P2 architecture, with series architecture, you name it. They will be able to do all that work by themselves under the strict control of CAE department. So it's a win-win, because engineering department will be able to deliver better design faster. CAE department will be able to focus on the next generation of modeling, and at the same time, they will be sure that people will use their model in the right way, not overstepping on the model, going outside of boundaries, because this is typically the kind of thing that can happen if you say, oh, I created model. Get the model and do whatever you want to do with it. This is a completely controlled way. And because we talked about collaborative work, and that's clearly a key enabler for successful numerical methodology deployment, let's look at the different community of users. Well, first, there is what we call the builder and the architecture. Earlier, we mentioned them as CAE engineers and the CAE department. Their main job is to create models, to create architecture, to share those architecture, because I demonstrated I showed you a video of system analyst, but the final GUI, of course, there is a dedicated GUI for people to go from the authoring model to the deployed model. Of course, they will have the responsibility of maintaining those components too. Then there are the end users that will perform a lot of run, have perfect applicative knowledge of what they need to do,
but probably in terms of modeling skills, well, that's not their prior concern, their main concern. So they don't have such a high modeling skill as the builders and architecture. Some might have, but not all. And they are trying to use the tool. And when I'm talking about the tool, I'm talking not only about the software, but the software and the models that has been created, because the biggest value in deploying this methodology is to be able to reuse the work that has been done internally. It's bigger than deploying simulation tools. It's deploying the models that have been created by your company that have cost money to your company, because, well, people that have created those models, I've been paid, I've spent time on it, I've used resources, whether it's computer or software. So it's a very good way to optimize ROI of simulation. And then there is a third category of people that are more, let's say, IT related, and that will maintain the tool in operating condition, and in some cases will create some specific scripts, some specific post-processing to ease the usage. And of course, because there are databases in the tool, you will need to have some people that are doing this maintenance, and there is no such a thing as a database deployment without the IT being involved in any company that is correctly structured. So to summarize, this is the main reason to move to this complete modeling deployment strategy. This is where you will be able to deal with multiple vehicle variants, multiple scenarios, and get a lot of results and compare all those results at once with synthesis criteria. So saying on vehicle 1 for scenario 2, okay, I will have a decent response, but clearly, if you look at this very simple smiley matrix, only the design 2 is able to achieve what is expected by the requirements for each scenario and each requirement or attributes. Also, it's a good way to deploy a de-skilled simulation platform. So you saw it in the second video. There is no need to be an expert in models because you don't see the models. Of course, the model is in the background, and an expert can get to this model directly one click away. You can download the model that has been generated and do a very detailed analysis of the model, or to stress this model if you know what you're doing. You will be able to cover multiple variants for analysis in multiple angles at once. And also something that is very important, everything is handled in revision, whether it's the parameterization, the type of model that you are using, everything is handled in revision, meaning that you have repeatability of your simulation and you have traceability. So if you are taking design decision based on simulation results, 5 years from now, you will be able to execute this simulation in the same condition and get the same results, even if the model has been modified in, and I hope the model will have been improved during those 5 years, but you will be able to get back to this original version of the model. And that's very, very important, especially when you see cases where people are facing aftermarket crisis, and you need to try to understand what went wrong and why, and how to correct this, and how to be sure that it will never happen again. And another thing that is very interesting is the fact that we are separating the models from the data. People that are responsible for the models are the CAE experts. People that are responsible for the data are the engineering departments. They know how to get this information. I mean, the design, is much easier to get when you are part of an engineering department than when you are part of a CAE department. By having those two different databases inside the platform, this is a clearly a separated responsibility of, this is my model, this is the data that will perform the model. The model can be wrong, the data can be wrong, but you know who is wrong if there is a problem, and you know who's responsible of what, and you will be able to share model if you are an expert in modeling, but also to share, I don't know, if I'm a transmission specialist and I created some parameterization of a gearbox, well, people from the vehicle department that needs to have a transmission in their model will be able to access to my parameterization and will not have to ask and run all over the transmission department to get the right parameters in terms of efficiency, of number of tools, or whatever you can think of. That pretty much concludes my presentation, and I think we have some time for questions.
Thank you, Mr. Desbrat, for touching on so many critical areas of vehicle designing and simulation. Now let's take some questions from the audience. So the first question is from Mr. Pranay. The question is, what happens to the systems that you test? Do they all find their way into a real prototype?
Of course not. And that's a very interesting question, because and this is where you might have a difference between the database that you will have into the deployment, the modeling deployment tool, and the database that you have into a PLM. Into PLM, you will have the definition of your final product. Here, we will have a traceability of many hypotheses, and those hypotheses are not intended to pollute the PLM database. So they will be stored, if you want, into this tool, and don't need to be pushed to the rest of the company, because, well, this is not a valid design or good enough design. And if at one point somebody is asking, well, why didn't we go this path for this architecture or this design, you will be able to retrieve this simulation and say, okay, this is why, because, well, this under this requirement or for these attributes, the results were not good enough. So that's why we selected a different design.
The next question is from Mr. Anis. So the question is, not all the vehicle models or variants are tested on the computer. What approaches do engineers take here?
Well, it was exactly the same problem with physical testing, except now it's happening earlier because of simulation. I have been an automotive engineer for more than 10 years before joining Siemens, and this is exactly the job that I was doing. What we were doing at the French OEMs was creating a coverage matrix, saying this variant will cover all those variants because it's more demanding on these attributes. So this is the variant that we are going to test for validating these attributes for this design. And the quality of this coverage matrix makes a huge difference in the terms of number of simulation or tests that you will have to perform. And this, to be exhaustive, this coverage matrix needs to also integrate tests at some point, saying, I will cover all of this by simulation, and then I will validate this with tests when prototype will be available. And this is how we do things. On the other hand, with the kind of tool that I just showed, it's now almost possible to do some brute force analysis, trying to evaluate all the variants at once in simulation. And if you have automated post-processing, you will be able to highlight the configuration that are raising problems.
So due to time constraint, we have to wrap up our session here. Thank you, Mr. Devadas, for sharing your insights.
It was a pleasure.
And with this, we have come to the end of this event. Thank you for joining ET Auto Masterclass.
Thank you very much.